If every ancient monument had collapsed, history would be much easier to explain. Instead, the ones that survived continue to challenge everything we think we know about the past. They were built by civilizations separated by oceans, languages, and thousands of years, yet many share the same astonishing precision, the same colossal stones, and the same engineering that still resists simple explanation. Some have endured powerful earthquakes, while modern buildings nearby crumbled. Others were placed in locations that remain difficult to access even today. Their craters left almost no instructions, only the silent evidence carved into rock. Every generation arrives believing it will finally solve these mysteries, yet each discovery reveals another layer of questions. Perhaps the ancient world is not hiding its secrets from us. Perhaps we are only beginning to understand the questions we should have been asking all along. At a bend of the Vonner River, about 28 kilometers southwest of Poitiers in western France, Sanxai preserves the remains of a Gallo-Roman complex whose engineering is far more difficult to explain than its quiet rural setting suggests. Across more than 25 hectares once stood temples, residences, water installations, and a theatre built for approximately 6,500 spectators. Yet much of the settlement now lies beneath fields, leaving only fragments of a much larger machine. The ruins had been known locally for centuries and were repeatedly stripped for reusable stone before systematic excavation began. In 1881, the Jesuit archaeologist Camille de la Croix arrived with around 15 workers and spent more than 2 years clearing large sections of the ancient settlement. Because he had only rented the land, many trenches were filled again when the campaign ended, burying structures that had barely been recorded. Later investigations between 1985 and 1994 revealed that several of his interpretations were incomplete, particularly his identification of the water complex as an ordinary Roman bathhouse. Sanxai reached its monumental peak during the 2nd century CE, when builders transformed the valley into a sanctuary serving worshippers, patients, and large public gatherings. The main sacred enclosure measured roughly 79 by 76 meters and surrounded an unusual octagonal temple. Across the river, an 89-meter-wide theatre was cut against the natural slope, reducing the amount of artificial support required while still providing space for thousands of spectators. The builders were not imposing a rigid urban grid on level ground. They were making 3 very different monuments function across uneven terrain divided by flowing water. The theatre offers one of the clearest examples of this calculated adaptation. Instead of constructing a vast freestanding framework, its cavea was pressed into the hillside and its walls were placed almost directly onto exposed bedrock after weaker surface layers had been removed. The masonry consisted largely of small limestone blocks cut into slightly tapered forms and laid in lime mortar, with occasional horizontal courses of fired ceramic material. Such bands could help level successive construction stages, distribute stresses and interrupt irregular cracking, while the limestone core remained thick enough to carry the timber seating once installed above it. This was not indestructible construction, but it was an economical system in which geology, wall geometry, and material selection compensated for the absence of massive foundations. The deeper mystery lies in the condition of the masonry that remains. Sanxai has endured roughly 18 centuries of rainwater penetration, plant growth, winter freezing, thermal expansion, and repeated human disturbance. Large quantities of stone were removed after antiquity, yet surviving walls still retain coherent faces, corners, channels, and pool outlines. Their durability cannot simply be attributed to unusually hard stone. The builders combined local limestone rubble, carefully fitted facing blocks, lime-based binders, and fired clay elements in walls designed to tolerate moisture rather than seal it completely. Lime mortar behaves very differently from modern Portland cement. It is relatively flexible, vapor-permeable, and capable of accommodating small movements without forcing stress into brittle stone. As freshly prepared lime reacts with atmospheric carbon dioxide, calcium carbonate gradually forms within the binder, strengthening it over time. Tiny cracks may sometimes close when moisture dissolves calcium compounds and redeposits carbonate inside the fracture, although no published scientific analysis has yet demonstrated unique self-healing formula specifically at Sangzai. The real technological question is therefore more subtle. How did regional builders select aggregate size, lime proportion, ceramic inclusions and wall thickness so effectively without chemical laboratories or standardized industrial materials? The occasional ceramic layers are especially important. Crushed brick and fired clay can react with lime to produce hydraulic compounds that harden more effectively in damp conditions, a principle repeatedly identified in studies of Roman and later historic mortars. Even when ceramic pieces were inserted as complete leveling courses rather than ground into powder, their porous surfaces improved mechanical bonding and helped control construction tolerances. At Sangzai, however, the precise composition of different mortars, the source of their lime, and the degree to which ceramic material contributed chemically, rather than structurally, remain insufficiently characterized in publicly available research. The walls survive, but the recipe behind their performance has not been reconstructed in full. Moisture management may have mattered as much as the mortar itself. The sanctuary stood beside a river and incorporated springs, pools, heated rooms, and drainage routes, exposing its masonry to repeated wetting and drying. Roman builders avoided relying on a single impermeable barrier. Water was redirected through slopes, channels, layered floors and voids, while breathable lime joints allowed trapped moisture to escape. In surviving walls, durability may result not from one miraculous substance, but from a complete system in which no component was forced to perform alone. Stone carried compression, mortar absorbed movement, ceramic courses corrected levels, and drainage reduced prolonged saturation. The octagonal temple demonstrates an even more deliberate relationship between water and structure. A spring emerged near the southeastern foundation of the sacred chamber, where large blocks were laid without tightly sealing every joint, apparently allowing water to be collected or pass through the foundation zone. This means that the builders may have designed the monument around a living hydraulic feature rather than attempting to eliminate it. Supporting a tall, sacred building above an active source required them to understand where pressure would accumulate, which materials could remain damp, and how water might be admitted without gradually washing the foundation apart. The so-called baths complicate the picture further. Archaeologists have identified at least 8 construction phases in this sector. Rooms were added, pools were altered, earlier sacred spaces were converted, floors were raised, and separate bathing installations were linked into an increasingly dense complex. Some expected elements of a conventional public bath are absent from the earliest phases, including a clearly organized cold room in one section. This has led researchers to reinterpret the building not simply as a civic therme, but as a sanctuary where immersion, heat, and healing rituals may have overlapped. From an engineering perspective, the repeated transformations are extraordinary. Every new pool increased the weight imposed on older walls. Each heated chamber changed local temperature and humidity. Raising a floor altered drainage gradients, while opening a passage through an existing structure could redirect forces into masonry never designed for the new arrangement. Yet the complex remained in use through successive modifications rather than being demolished and rebuilt from the ground up. The builders appear to have understood the hidden capacity of older foundations well enough to reuse them, but no calculations, construction manuals, or regional building records explain how those decisions were made. The heating system would also have required careful control. Furnaces sent hot gases beneath raised floors supported on small pillars and sometimes through hollow wall elements. If passages were too narrow, smoke and heat would stagnate near the furnace. If they were too large, the gases would cool before reaching distant rooms. Floors had to resist concentrated loads while remaining thin enough to transmit heat. At Sangsai, the challenge was intensified by continuous renovation, because new heated areas had to connect with older spaces whose original airflow had already been established. Even the theatre's strange plan resists a simple explanation. Its seating curve extends beyond the normal semicircle of a classical Roman theatre, while the orchestra is nearly circular and the stage structure appears comparatively small. It belongs to a group of mixed Gallo-Roman performance buildings that combined features of theatres and amphitheatres, possibly allowing ceremonies, dramatic performances, and more physical spectacles within the same enclosure. The structure was therefore not merely copied from an imperial model, it was redesigned for regional use. Yet the practical rules governing sightlines, crowd movement, and acoustics have not survived. Do you think modern engineers could faithfully reproduce Sangsai using only the tools and knowledge available nearly 2,000 years ago? Share your thoughts in the comments below. The Sukur cultural landscape lies in the Mandara Mountains of northeastern Nigeria, near the border with Cameroon, and at first glance appears to be little more than a maze of stone terraces climbing a steep hillside. Yet this UNESCO World Heritage Site preserves one of Africa's most sophisticated examples of pre-industrial engineering, where architecture, metallurgy, hydrology, and landscape design were combined into a single functioning system centuries before modern surveying equipment existed. The greatest mystery is not what Sukur's builders created, but how they mastered technologies whose practical details have largely disappeared. Unlike many archaeological discoveries uncovered beneath deep layers of sediment, Sukur never truly vanished from the landscape. Local communities continued to occupy the surrounding region, but systematic archaeological and anthropological investigations during the 20th century revealed that the mountain settlement represented far more than a traditional village. Detailed surveys documented an extensive network of dry stone walls, ceremonial structures, agricultural terraces, roads, iron smelting remains, and hydraulic features spread across the mountainside. In 1999, UNESCO recognized Sukur as the first Nigerian cultural landscape to receive World Heritage status, citing the exceptional preservation of an integrated technological and cultural system that had evolved over many centuries. Among every surviving feature, the evidence of iron production raises the greatest unanswered questions. Long before European industrial metallurgy reached West Africa, Sukur had already become an important regional centre for iron manufacture. Excavations have uncovered numerous furnace bases, slag deposits, tuyere fragments, charcoal concentrations, and forged iron artifacts, demonstrating that metallurgy formed the economic foundation of the settlement. Chemical studies of the slag indicate repeated smelting campaigns rather than isolated experiments, while radiocarbon dating places significant phases of iron production roughly between the 13th and 16th centuries, although iron working in the Mandara region almost certainly began earlier. The challenge is that successful bloomery smelting requires a remarkably precise balance of variables. Iron oxides must be reduced at temperatures approaching approximately 1,100 to 1,300 degrees Celsius. Below this range, metallic iron fails to separate efficiently from the ore. Above it, the bloom may absorb excessive carbon or the furnace structure itself begins to deteriorate. Maintaining such conditions demands continuous control of airflow, fuel consumption, furnace geometry, and ore composition without thermometers, pressure gauges, or modern refractory materials. What continues to puzzle archaeometallurgists is how Suker's metalworkers achieved this consistency on a rugged mountainside. The surviving furnaces are relatively modest in size, yet slag analysis suggests prolonged operation under stable thermal conditions. Some researchers propose that the builders intentionally positioned furnaces where seasonal mountain winds accelerated naturally through narrow passages, creating a self-regulating draft that reduced dependence on continuous manual bellows operation. Others argue that carefully engineered tuyères introduced air into the combustion chamber at specific angles, increasing combustion efficiency while minimizing heat loss. Neither explanation has been demonstrated conclusively because the upper portions of the furnaces have almost entirely disappeared, leaving only their lower foundations and scattered fragments. The missing architectural elements may have contained precisely the engineering features responsible for their remarkable performance. Fuel management introduces another layer of complexity. Producing bloomery iron consumes enormous quantities of high-quality charcoal. Experimental archaeology has shown that several kilograms of charcoal may be required to produce a single kilogram of usable iron, depending on ore quality and furnace efficiency. Such demand would normally threaten rapid deforestation, yet paleo-environmental evidence suggests that the Sukur region sustained iron production for generations without complete ecological collapse. Researchers suspect that woodland resources were managed through controlled harvesting cycles, but direct evidence remains limited. Whether the community consciously practiced long-term forest management or benefited from favorable environmental conditions remains unresolved, making Sukur an unusually early example of potentially sustainable heavy industry. The ore itself presents additional questions. Geological surveys identify iron-bearing formations within reachable distance of the settlement, but the mineral quality varies considerably. Successful bloomery technology requires more than simply collecting reddish stones from the landscape. Experienced smelters must recognize ore with appropriate iron concentrations, while avoiding excessive impurities such as silica or phosphorus that reduce bloom quality. No written manuals survive to explain how Sukur's craftsmen selected, sorted, roasted or prepared their ore before smelting. Yet the surviving slag demonstrates that these choices were consistently effective over long periods. This level of accumulated empirical knowledge rivals metallurgical traditions documented elsewhere in Africa, including those of the Haya people in present-day Tanzania, whose furnaces achieved exceptionally high thermal efficiencies. Whether similar technological principles evolved independently in Sukur or spread through regional exchange networks remains an active subject of debate. Equally remarkable is the integration of metallurgy into the settlement's overall design. Iron production was not isolated in a distant industrial district, but carefully positioned within a landscape already constrained by steep slopes, residential compounds, ceremonial spaces, livestock enclosures, and agricultural terraces. Furnaces required access to ore, water, charcoal, labor, and ventilation, while simultaneously minimizing fire hazards to nearby structures. The spatial organization suggests deliberate planning rather than gradual accumulation. Even today, archaeologists cannot fully reconstruct the decision-making process that determined why each production area occupies its specific location on the mountain. Beyond metallurgy, Sukur displays an equally sophisticated understanding of stone engineering. Hundreds of dry stone retaining walls stabilize terraces across gradients that would normally experience severe erosion during Nigeria's intense rainy seasons. Many walls remain standing despite centuries of seasonal weathering, even though they contain no mortar whatsoever. Instead, builders selected individual stones whose shapes lock together under compression, distributing weight laterally while allowing minor movement during ground settlement. Modern geotechnical engineers recognize this flexibility as one reason dry stone structures can outperform rigid masonry under changing environmental conditions. Yet the builders achieved it entirely through experience rather than mathematical structural analysis. The agricultural terraces reveal another level of engineering intelligence. Rather than cutting broad horizontal platforms, the inhabitants created narrow stepped fields that slowed runoff, trapped fertile sediment, reduced slope instability, and increased moisture retention. Remote sensing and topographic studies indicate that these terraces function as interconnected hydraulic units rather than isolated plots. Water descending the mountain loses velocity as it encounters successive retaining walls, dramatically reducing erosive force before reaching lower elevations. Such integrated landscape management resembles principles employed in several of the world's great terrace civilizations, although Sukur developed under very different environmental and cultural conditions. Water management itself remains surprisingly understated. Visitors expecting monumental aqueducts or large reservoirs often overlook the ingenuity hidden within the terrain. Instead of forcing water through conspicuous channels, Sukur relies on subtle stone-lined pathways, natural fractures, carefully graded surfaces, and drainage gaps incorporated into retaining walls. During heavy rainfall, runoff disperses through numerous small routes rather than concentrating into destructive torrents. The entire mountainside functions as a distributed hydraulic network, one that becomes visible only when examined as an integrated engineering system instead of a collection of individual structures. Do you think Sukur's lost ironworking techniques and engineering knowledge could ever be fully reconstructed? Or has part of that ancient expertise disappeared forever? Share your thoughts in the comments below. Beneath the quiet countryside of Normandy in northern France lies Vieux-la-Romaine, the ancient Roman city of Aragenua, where streets, villas, drainage systems, and remarkably vivid wall paintings have survived almost 2,000 years, leaving archaeologists with a question that grows more intriguing every decade. How did a provincial city preserve engineering and artistic achievements that still challenge modern understanding? The forgotten city remained buried for centuries after its gradual decline during the late Roman Empire, until systematic excavations accelerated during the 19th and 20th centuries, with major archaeological campaigns after the 1980s exposing nearly 20 hectares of an urban landscape that once covered approximately 35 hectares. Excavations uncovered forums, bath complexes, workshops, elite residences, underground drainage, and one of the best preserved Roman domestic quarters in northern Gaul, providing an unusually complete laboratory for studying Roman urban technology rather than isolated monuments. At first glance, Aragenua appears to be another carefully planned Roman town, yet the precision hidden beneath its streets immediately raises difficult engineering questions. Surveyors laid out an orthogonal street network whose alignment remained consistent across hundreds of meters, despite the absence of optical instruments, satellite positioning, or modern leveling equipment. Roman engineers are believed to have relied upon the groma for right angles and the chorobates for measuring gradients. Yet, experimental archaeology continues to demonstrate how demanding it would have been to maintain such accuracy across an expanding city where even a slight cumulative error could have distorted the entire street grid. Beneath the visible architecture, underground drains were constructed with gradients generally estimated between roughly 0.5% and 2%. allowing wastewater to flow continuously without excessive erosion or stagnation. Remarkably, many sections still preserve their original inclination despite nearly 2 millennia of soil movement, suggesting that Roman builders possessed a practical understanding of terrain stabilization, far exceeding what written sources describe. The city's largest residences reveal another layer of technological sophistication. The House of the Grand Peristyle occupied nearly 1,500 square meters, organized around an open central courtyard that naturally distributed daylight while encouraging air circulation throughout the surrounding rooms. Modern architects describe similar principles as passive climate control, yet Roman builders achieved them entirely through orientation, geometry, and carefully calculated proportions. Even more impressive is the hypocaust heating system concealed beneath the floors. Hundreds of small brick pillars supported elevated pavements, while hot air generated by furnaces circulated beneath living spaces before rising through hollow wall flues. Maintaining relatively even temperatures across multiple rooms required balancing airflow, chamber volume, and exhaust efficiency without mathematical fluid dynamics or mechanical regulators. Archaeologists can reconstruct the structure itself, but the precise empirical knowledge guiding its design remains largely invisible because the calculations, if they ever existed in written form, have not survived. The masonry surrounding these buildings introduces another unresolved puzzle. Numerous walls still retain extraordinary structural integrity because Roman builders combined lime with crushed ceramic fragments and carefully selected aggregates to create mortars capable of continuous mineral reactions long after construction had finished. Recent materials science has demonstrated that lime clasts embedded within certain Roman mortars can dissolve and recrystallize when exposed to moisture, naturally sealing microscopic fractures before they propagate into larger structural failures. While this process has now been documented in laboratory studies, reproducing the remarkable consistency achieved by ancient craftsmen remains challenging because subtle variations in firing temperatures, aggregate selection, and mixing techniques dramatically influence long-term durability. The walls standing beneath the Norman soil therefore represent not merely ancient construction, but the accumulated result of practical knowledge refined across generations without modern chemistry. Yet none of these achievements equals the mystery preserved inside the city's painted rooms. When archaeologists entered several elite houses, fragments of wall decoration still displayed vibrant reds, deep blacks, brilliant yellows, and delicate greens despite lying underground for nearly 2,000 years. Pigments are expected to fade through oxidation, microbial activity, moisture, salt crystallization, and repeated seasonal temperature changes. Instead, many frescoes retained astonishing color saturation, allowing researchers to reconstruct decorative schemes with unexpected confidence. Scientific analysis has identified mineral pigments, including red ochre rich in hematite, yellow ochre containing hydrated iron oxides, carbon black derived from incomplete combustion, calcium carbonate whites, and occasionally the expensive copper-based pigment known as Egyptian blue. None of these materials alone explains the extraordinary preservation. The true secret lies within the interaction between pigment, plaster, chemistry, and timing. Roman painters employed the fresco technique by applying pigments onto freshly laid lime plaster before carbonation transformed the wet surface into solid calcium carbonate. As the plaster absorbed atmospheric carbon dioxide, microscopic calcite crystals gradually formed around pigment particles, physically locking them into the wall itself rather than leaving them as a fragile surface coating. The painting therefore became part of the architecture instead of resting upon it. Modern conservation scientists using scanning electron microscopy have observed this intimate mineral bond at microscopic scales, Yet, laboratory replication rarely produces precisely the same long-term stability. The quality depended upon countless variables including lime purity, particle size, moisture content, drying speed, ambient humidity, and the exact interval between plaster application and painting. Ancient craftsmen managed these variables entirely through experience rather than analytical instruments. Some colours present even deeper puzzles. Egyptian blue, widely regarded as the world's first synthetic pigment, required heating silica, copper compounds, calcium sources, and alkali fluxes to temperatures approaching 850 to 1000 degrees Celsius until crystals of cuprorivite formed. Producing the pigment demanded controlled firing conditions, remarkably advanced for antiquity. Under visible light, the colour appears modest, yet modern infrared imaging reveals that Egyptian blue emits powerful luminescence invisible to the human eye, allowing researchers to detect microscopic traces even where the original surface seems blank. Every surviving fragment demonstrates that Roman artists understood not merely aesthetic decoration, but industrial-scale material production, involving chemistry that would remain unmatched in Europe for centuries. Equally remarkable is the deliberate preparation of the plaster beneath the paint. Instead of a single layer, walls often consisted of multiple coats progressing from coarse aggregate to increasingly refined lime finishes. Each layer reduced internal stress while creating a stable surface capable of resisting cracking as the building expanded and contracted with seasonal temperature changes. The final polished surface reflected light softly across painted rooms, enhancing colour intensity without artificial illumination. Even after centuries underground, microscopic examination frequently reveals that individual plaster layers remain firmly bonded, evidence of exceptional craftsmanship rarely appreciated by visitors observing only the surviving pigments. Perhaps the greatest mystery is that these paintings survived not because they escaped history, but because history buried them. As buildings collapsed and later sediments gradually sealed the interiors from sunlight, oxygen fluctuations, and mechanical damage, the walls entered an accidental conservation chamber. Yet burial alone cannot explain why neighbouring fragments often display dramatically different preservation, despite experiencing nearly identical environmental conditions. Researchers continue investigating how local groundwater chemistry, soil composition, microbial populations, and original construction methods interacted over centuries to determine which colours endured and which vanished forever. Every excavation, therefore, becomes both an archaeological discovery and a scientific experiment extending across 2 millennia. Do you think the Romans truly understood material science far better than we usually give them credit for? Or are there still lost techniques waiting to be rediscovered? Share your thoughts in the comments below. Located in the forests of southwestern Georgia, United States, Kolomoki Mounds appears at first to be nothing more than a cluster of grassy hills. Yet beneath those quiet earthworks lies one of the largest ceremonial centers ever constructed in eastern North America. A place where thousands of people reshaped an entire landscape nearly 16 centuries ago without metal tools, wheeled transport, or written engineering manuals, leaving behind geometric precision and astronomical knowledge that continue to challenge archaeologists. The existence of Kolomoki first attracted scholarly attention during the 19th century, but systematic excavations led by archaeologist William Sears between 1948 and 1953 transformed it from an overlooked mound complex into one of the most significant archaeological sites of the woodland period. Radiocarbon dating, ceramic analysis, and stratigraphic studies indicate that the main construction phase occurred between approximately 350 and 600 AD, when the site covered more than 2 square kilometers and served as a major ceremonial centre for communities spread across the lower Chattahoochee Valley. What immediately separates Kolomoki from hundreds of other mound sites is not simply its scale, but its extraordinary planning. 7 major platform and burial mounds were positioned around an immense central plaza, with several smaller mounds completing a layout that appears intentional rather than organic. Survey measurements reveal remarkably consistent spatial relationships extending across several hundred meters. Achieving that level of alignment required far more than simply piling soil into hills. Every platform had to maintain controlled elevation, stable slopes, and carefully defined boundaries over terrain that naturally rises and falls. Modern engineers would rely on optical instruments, benchmarks, and repeated topographic measurements to accomplish such work. Yet no evidence has been found for comparable surveying technology. Archaeologists continue to debate whether the builders employed sophisticated rope-based geometry, astronomical references, or surveying methods that disappeared without leaving recognizable tools. Even more remarkable is the sheer volume of earth that had to be moved. Estimates suggest that the largest mounds collectively required between 200,000 and 250,000 cubic meters of soil, representing well over 300,000 metric tons of material transported entirely by human labor. Experimental archaeology has demonstrated that a single woven basket typically carried only 20 to 30 kilograms of earth. At that rate, constructing the complex would have required millions of individual transport cycles. Such numbers imply years, perhaps decades, of coordinated labor involving hundreds or even thousands of workers, yet excavations have uncovered no evidence for an empire, military administration, or centralized bureaucracy capable of enforcing projects on this scale. The engineering survived, but the organizational system behind it vanished completely. Excavations inside the mounds reveal another technical puzzle hidden beneath the surface. Rather than consisting of randomly dumped soil, the earthworks were built from repeated layers of clay, sandy loam, and compact sediments placed in deliberate sequences. Geotechnical studies indicate that alternating these materials improves drainage, while reducing internal deformation caused by seasonal moisture changes. Some layers appear intentionally compacted before additional fill was added above them, producing structures that have remained recognizable for nearly 16 centuries despite intense rainfall, root penetration, biological activity, and repeated freeze-thaw cycles. Modern soil mechanics explains why such layering works, but it does not explain how prehistoric builders discovered these principles through observation alone, or maintained consistent construction standards generation after generation. The greatest mystery, however, stands inside what archaeologists designate as Mound E, where a discovery made during Sears excavations sparked one of the longest-running debates in North American archaeology. Beneath the mound, researchers uncovered a circular arrangement of post holes, unlike those associated with ordinary buildings. Sears proposed that these wooden posts once formed a solar observatory capable of tracking the annual movement of sunrise across the horizon. According to his reconstruction, an observer standing at a designated viewing point would see the rising sun align with specific posts during the summer solstice, winter solstice, and the spring and autumn equinoxes. If correct, the arrangement transformed an ordinary ceremonial structure into a sophisticated astronomical instrument capable of marking the changing seasons with surprising precision. This interpretation immediately raised difficult questions because the geometry is not impossible by accident. The sun's rising position shifts by nearly 47 degrees along the horizon over the course of a year at Kolomoki's latitude, reaching its northernmost and southernmost extremes only during the solstices before reversing direction. Identifying those turning points requires continuous observations extending over many annual cycles. A single year is insufficient because atmospheric refraction, weather conditions, and local horizon irregularities introduce observational errors. Ancient observers would have needed decades of repeated measurements before confidently identifying the exact limits of the solar cycle. Such long-term astronomical recording implies an institutional tradition capable of preserving observations across generations, yet no written records exist to explain how this knowledge was transmitted. Later researchers revisited Sear's hypothesis using improved surveying equipment and computer simulations. Some concluded that several alignments remained statistically meaningful, while others argued that reconstruction uncertainties made definitive conclusions impossible because many original wooden posts had decayed long before excavation. Even slight shifts of a few centimeters in reconstructed post positions can alter apparent alignments by several degrees across distant horizons. Critics therefore caution against overstating the astronomical evidence, while supporters argue that the overall pattern exceeds what random placement would produce. More than half a century after the proposal was first published, neither side has completely resolved the debate, making Kolomoki one of the rare archaeological sites where the central question remains genuinely open rather than simply romantic speculation. Regardless of whether every proposed alignment proves correct, the builders clearly demonstrated a deep awareness of celestial cycles. Several mound axes and plaza orientations differ systematically from the surrounding landscape, instead of simply following convenient topography. Researchers have suggested that these orientations may relate to sunrise positions, seasonal ceremonies, or agricultural calendars that synchronized planting and harvesting with predictable solar events. Such interpretations remain hypotheses, yet they illustrate how architecture, ritual, and astronomy may have formed a single integrated system rather than independent activities. The precision of the landscape becomes even more intriguing when viewed from above. Modern aerial photography and LiDAR mapping reveal subtle geometric relationships almost impossible to recognize from ground level. The builders maintained broad open spaces between major earthworks, preserving uninterrupted sightlines across the central plaza. Those clear visual corridors would have been essential if observations depended on watching the sun rise against distant horizon markers. Whether intentional or coincidental, the spatial organization repeatedly favors visibility over convenience, suggesting that empty space itself formed part of the site's design. Kolomoki also raises unanswered questions about prehistoric mathematics. Constructing symmetrical platforms hundreds of meters apart while preserving consistent orientation requires practical understanding of distance measurement, angle estimation, and geometric planning. Unlike stone architecture, where errors can often be corrected block by block, massive earthen monuments become increasingly difficult to reshape once thousands of tons of soil have been deposited. Mistakes made early in construction would have multiplied as each additional layer was added. The finished earthworks show surprisingly little evidence of such cumulative errors, implying careful planning before construction even began. Do you think Mound E was truly an ancient solar observatory, or does Kolomoki still hide an even greater engineering secret? Share your thoughts in the comments below. The Temple of Fortuna Primigenia stands above the modern town of Palestrina, about 35 kilometers east of Rome, as one of the largest religious complexes ever built by the Roman Republic. Long before Imperial Rome raised the Colosseum or the Pantheon, engineers here reshaped an entire limestone hillside into an immense sequence of terraces, stairways, retaining walls, vaulted chambers, and ceremonial plazas. More than 2,000 years later, archaeologists still debate not why the sanctuary was sacred, but how a civilization without modern surveying instruments, geotechnical science, or powered machinery transformed an unstable mountain into an architectural system that has survived earthquakes, erosion, and centuries of rebuilding. Its existence had never been completely forgotten because medieval buildings occupied much of the ancient terraces, but the true scale of the sanctuary remained hidden until extensive excavations began after Allied bombing during the Second World War destroyed large sections of Palestrina in 1944. Beneath the collapsed Renaissance structures, archaeologists uncovered enormous concrete substructures, vaulted galleries, monumental staircases, and retaining walls that revealed an engineering achievement far beyond earlier expectations. Further excavations confirmed that most of the sanctuary had been constructed between approximately 120 and 80 BCE, making it one of the earliest monumental examples of Roman concrete architecture. The greatest mystery begins with the mountain itself. Greek sanctuaries usually adapted their buildings to the landscape, but the builders of Fortuna Primigenia attempted something fundamentally different. Instead of placing a temple on a summit, they converted nearly the entire hillside into an artificial architectural machine. The sanctuary extends across a vertical rise of roughly 50 meters and stretches almost 300 meters from its lowest terraces to the upper sanctuary. Every visible platform conceals layers of retaining structures, filled embankments, vaulted corridors, drainage passages, and supporting chambers buried deep inside the slope. Modern engineers recognize this as an immense earth-retaining system rather than a collection of isolated buildings, yet the calculations required for such stability remain difficult to explain. Today, geotechnical engineers evaluate slope safety using soil cohesion, friction angles, groundwater pressure, and numerical modeling before excavation begins. Roman builders possessed none of these mathematical frameworks, yet the mountain they reshaped has remained remarkably stable for over 2 millennia, despite repeated seismic activity in central Italy and centuries of weathering. Excavations reveal that enormous quantities of bedrock were removed before construction even started. Archaeologists estimate that tens of thousands of cubic meters of limestone had to be quarried directly from the hillside to create the stepped platforms visible today. Without explosives, hydraulic excavators, or steel machinery, workers relied on iron picks, wedges, hammers, chisels, and controlled fracturing of the rock. The astonishing question is not whether such excavation was possible, but how planners maintained precise geometric alignment while continuously altering the mountain beneath their own construction. Every new terrace depended upon the stability of the one below it. A single major miscalculation could have triggered progressive collapse across the entire complex, yet no evidence suggests catastrophic structural failure during antiquity. What makes this even more remarkable is that the sanctuary functions less like architecture and more like a massive retaining wall disguised as a religious monument. Behind almost every visible facade lies another hidden structural layer. Thick concrete walls absorb horizontal pressure from the hillside, while barrel vaults distribute loads into adjoining supports rather than concentrating stress at isolated points. Modern structural analysis has demonstrated that arches dramatically reduce bending forces by converting vertical loads into compression. But this principle was being exploited here generations before Roman engineering reached its classical imperial peak. The sanctuary, therefore, represents not merely decorative architecture, but an early experiment in large-scale structural mechanics whose underlying design philosophy appeared centuries ahead of its time. The concrete itself introduces another unresolved puzzle. Temple of Fortuna Primigenia is among the earliest surviving monuments to employ opus caementicium on such an extraordinary scale. Instead of carving every structural element from stone blocks, Roman engineers poured concrete between masonry facings, producing walls capable of carrying enormous loads while reducing construction time. Scientific analysis of surviving Roman concrete from the Republican period has identified mixtures containing lime, volcanic ash known as pozzolana, and volcanic aggregates that chemically reacted with water to form durable calcium aluminum silicate hydrates. Recent mineralogical studies published in journals including Science Advances have demonstrated that certain Roman concretes continued strengthening through long-term mineral reactions and even displayed forms of self-healing as lime clasts reacted with infiltrating water. Whether exactly the same mechanisms operated within the earliest concrete used at Fortuna Primigenia remains uncertain because the composition varies between construction phases, yet many structural cores continue supporting massive loads after more than 2,000 years with surprisingly limited degradation. Equally intriguing is the network hidden beneath the ceremonial terraces. A mountain naturally accumulates groundwater, and hydrostatic pressure behind retaining walls is among the greatest causes of structural collapse in ancient masonry. If rainwater had been trapped behind the sanctuary's walls, increasing pressure would eventually have displaced entire sections downhill. Instead, the complex survived centuries of seasonal rainfall. Archaeologists have documented channels, culverts, drainage galleries, and internal passages that redirected water away from critical foundations, although significant portions of the hydraulic network remain inaccessible beneath later construction. The complete drainage system has never been fully reconstructed, leaving unanswered how Roman engineers calculated water flow through such an enormous artificial hillside without hydraulic equations or modern surveying equipment. Visitors climbing through the sanctuary today experience an overwhelming sense of symmetry, yet this apparent simplicity conceals another engineering challenge. The monumental central staircase aligns successive terraces, porticos, plazas, and finally the upper sanctuary along a remarkably consistent axial plan despite the irregular topography beneath. Surveyors now rely on total stations, satellite positioning, laser scanning, and digital terrain models to maintain such geometric accuracy across steep landscapes. Roman agrimensurers possessed only ropes, measuring rods, plumb lines, water levels, and the groma. Nevertheless, the sanctuary demonstrates an exceptional command of spatial planning over hundreds of meters of changing elevation. Archaeological measurements indicate only minimal cumulative deviation across the principal architectural axis, suggesting surveying precision that still surprises specialists studying Republican engineering. Another mystery concerns the extraordinary number of vaulted chambers concealed within the terraces. These spaces were not simply storage rooms. Many functioned as structural voids, reducing the weight of the artificial embankments while simultaneously transferring loads through compression into deeper foundations. This strategy resembles modern approaches to reducing dead load within large retaining structures. Yet no surviving Roman technical treatise explains how designers determined the dimensions, spacing, or sequence of these chambers. Vitruvius wrote about architecture nearly a century later, leaving the original engineering methods employed at Fortuna Primigenia largely undocumented. Modern conservation projects employing laser scanning, photogrammetry, and structural monitoring continue revealing new details about the sanctuary's internal organization. Digital reconstructions increasingly demonstrate that every terrace, retaining wall, vault, staircase, and plaza belong to a single integrated engineering concept rather than independent construction campaigns. Even so, the mathematical principles guiding that concept remain largely invisible. The builders left no construction manuals, no design drawings, and no written explanation of how they transformed a steep mountain into one of, of antiquity's most ambitious architectural systems. Casinomegas is located beneath the quiet village of Chassenon in western France and represents one of the largest Roman monumental complexes ever built in Gaul. At first glance, it appears to be another provincial archaeological site, yet beneath its collapsed walls survives an engineering system so sophisticated that modern researchers are still reconstructing how it functioned almost 2,000 years ago. The ruins were already known to local inhabitants during the Middle Ages, when enormous Roman stones were reused in churches and nearby buildings. But the true scale of Casinomegas remained hidden until systematic excavations began during the 19th century and expanded dramatically through archaeological campaigns from the 1960s onward. Ground-penetrating surveys, laser scanning, architectural reconstruction and thermal simulations have since revealed that what once appeared to be scattered ruins actually belonged to one of the most ambitious bath complexes anywhere in the western provinces of the Roman Empire. The first mystery begins beneath the foundations rather than above them. Casinomegas was constructed directly on the fractured rocks of the Rocha Chouart impact structure, formed approximately 200 million years ago when an asteroid estimated at 1 to 1.5 kilometers in diameter struck what is now southwestern France. Instead of ordinary limestone, Roman builders encountered impact breccias, shattered crystalline rocks, and irregular geological layers produced by one of Europe's largest known meteorite impacts. Modern engineers normally regard fractured bedrock as difficult terrain for supporting extremely heavy masonry, because uneven settlement can crack vaults and walls over time. Yet the Roman architects covered this unstable geological platform with monumental buildings whose foundations have remained remarkably stable for nearly 20 centuries. Archaeologists still debate how Roman surveyors evaluated such unpredictable ground without modern geotechnical instruments, because no evidence survives describing how they selected precisely which fractured zones could safely bear thousands of tons of stone. The greatest engineering puzzle, however, lies beneath the floors rather than inside the walls. Casinomegas contains one of the largest surviving hypocaust systems ever discovered in Western Europe, a heating network whose scale exceeds what many historians once believed possible for a provincial town. Instead of relying on fireplaces inside occupied rooms, enormous furnaces generated hot air that travelled through a labyrinth hidden beneath suspended floors. Hundreds of small brick pillars, known as pillae, supported thick pavements while leaving continuous cavities underneath. Heat circulated through these chambers before climbing inside hollow, ceramic wall flues, warming entire rooms from below and along their walls simultaneously. The principle itself is well understood, but the extraordinary dimensions of the Casinomegas installation continue to raise questions that remain only partially answered. The preserved bath complex occupies roughly 1.5 hectares, making it among the largest Roman thermal establishments outside Italy. Archaeological excavations have documented extensive furnace rooms, long underground heating corridors, multiple service passages, and dense forests of brick supports extending beneath vast areas of flooring. Maintaining comfortable temperatures across such an enormous building was not simply a matter of producing more fire. Different rooms demanded carefully controlled environments. The caldarium required temperatures that may have approached 50 degrees Celsius, while the tepidarium needed significantly lower heat, and the frigidarium had to remain relatively cool despite standing only meters away. Modern computational fluid dynamics has been applied to reconstruct airflow through surviving structures, yet no model has fully explained how Roman engineers balanced temperature, airflow velocity, pressure, and fuel efficiency across the entire complex without overheating some chambers, while leaving others cold. Even more remarkable is the apparent stability of this thermal network over centuries of operation. Every heating cycle subjected masonry to continuous expansion and contraction as temperatures fluctuated day after day. Such thermal stress normally produces fractures, particularly across large spans of stone flooring. Instead, much of the surviving substructure displays surprisingly limited structural deformation. Researchers suggest that the Romans carefully selected layered construction techniques combining stone foundations, mortar bedding, brick supports, suspended floors, and air cavities that distributed both mechanical loads and thermal expansion. The exact proportions of the mortars used throughout Casino Magus remain under study because chemical analyses indicate mixtures containing lime, crushed ceramics, and aggregates whose composition varies according to structural function. Some specialists believe these changing recipes were intentionally adapted to withstand repeated heating cycles, although no surviving Roman manual describes such engineering decisions in detail. The hidden passages beneath the baths introduce another mystery that rarely receives attention. These were not narrow crawl spaces built only for hot air circulation. Many corridors were large enough for workers to enter, remove accumulated ash, inspect furnaces, repair damaged supports, and regulate combustion without interrupting activity above. In effect, Roman engineers created an underground maintenance level, almost entirely concealed from bath visitors. This separation between public architecture and hidden technical infrastructure resembles concepts commonly associated with modern mechanical buildings rather than ancient civic monuments. The sophistication of this service network suggests that long-term maintenance had been incorporated into the original architectural design, rather than added later as an improvisation. Fuel consumption presents another unanswered question. Experimental reconstructions of Roman bath complexes indicate that installations of comparable size could require several tons of firewood each day to sustain operating temperatures, especially during colder seasons. Supplying such quantities continuously would have demanded organized forestry, transportation, storage facilities, trained furnace operators, and precise scheduling. Casino Magus was not Rome, Alexandria, or Carthage. It occupied a provincial landscape, making its enormous energy requirements increasingly difficult to reconcile with traditional assumptions about the settlement's size and economic importance. Some archaeologists argue that the complex served pilgrims, merchants, and travelers moving along major Roman roads rather than only local residents, while others suggest it represented a regional administrative center whose true population has been underestimated. Neither interpretation fully explains why such an exceptionally large thermal installation was constructed so far from the empire's largest urban centers. Water management forms another layer of uncertainty. Roman baths depended upon continuous supplies of clean water, while simultaneously removing enormous volumes of wastewater. Excavations have identified reservoirs, drainage channels, distribution conduits, and sophisticated sewer systems integrated throughout the complex. Nevertheless, parts of the hydraulic network remain missing, preventing researchers from reconstructing the complete circulation system. Questions remain regarding the precise origin of the freshwater supply, the total daily volume delivered, and the hydraulic mechanisms that maintained sufficient pressure across different sections of the baths. Considering the immense quantities of heated water required every day, the incomplete preservation of this infrastructure leaves one of the most important engineering systems only partially understood. The visible ruins today represent only a fraction of the original monument because most vaults and upper walls collapsed long ago. Yet, surviving foundations demonstrate extraordinary precision in distributing loads across irregular bedrock. Large vaulted halls once rose above spaces now open to the sky, their immense weight transferred through carefully positioned walls and substructures that continue to stand despite centuries of weathering. Laser surveys have revealed geometric consistency across the remaining masonry, suggesting Roman builders achieved remarkable construction accuracy over a vast architectural footprint using surveying instruments far simpler than those available today. Bagacum Nerviorum, located beneath the modern town of Bavay in northern France, was once the capital of the Roman Civitas Nerviorum and one of the most ambitious engineering projects on the empire's northwestern frontier. What survives today appears almost ordinary: buried walls, fragments of streets, and the immense outline of a forum. Yet every excavation has revealed the same unsettling contradiction. This monumental city was erected on terrain that modern engineers would hesitate to choose for buildings of such weight, and after nearly 2,000 years, much of its structural geometry remains remarkably stable. Bagacum was identified during antiquarian investigations in the 18th century, but systematic archaeological excavations accelerated throughout the 19th and 20th centuries after large Roman foundations repeatedly appeared beneath Bavay streets. Excavations eventually exposed an enormous public complex covering nearly **2, 5 hectares **, making it one of the largest known forums in the Western Roman provinces. Coins, inscriptions, ceramics, construction techniques, and dendrochronological evidence place its principal expansion between the late 1st and 2nd centuries AD, when Bagacum became the administrative center of the Nervii under Roman rule. The sheer size of the city immediately raises questions. The forum alone measured approximately **, 240 meters by 110 meters **, dimensions rivaling monumental civic spaces in far larger provincial capitals. Archaeologists estimate that the urban population probably fluctuated between **, 10,000 and 20,000 inhabitants **. Yet the civic infrastructure appears designed for a settlement with considerably greater administrative responsibilities. The scale suggests that Roman planners envisioned Bagacum not merely as a town, but as a logistical heart connecting northern Gaul with the Rhine frontier. 7 major Roman roads radiated from the city toward Cologne, Trier, Tongeren, Amiens, Reims, Boulogne, and Kassel, transforming Bagacum into one of the most strategically connected transport hubs in Roman Europe. Even so, transportation networks alone do not explain why such extraordinary engineering resources were concentrated here. The greatest mystery begins beneath the city rather than above it. Unlike many celebrated Roman sites constructed directly on competent bedrock, Bagacum occupied terrain dominated by **, clay-rich sediments, unconsolidated alluvial deposits, and a relatively high groundwater table **. These conditions are notoriously unfavorable for supporting massive masonry structures because clay compresses unevenly, retains moisture, expands during wet periods, contracts during drought, and gradually transfers loads through slow consolidation. Modern civil engineering generally requires extensive geotechnical investigation before placing heavy stone buildings on comparable ground. Yet Roman engineers accomplished precisely that almost 2 millennia before soil mechanics became a scientific discipline. Archaeological excavations beneath the forum have revealed sophisticated foundation systems, composed of successive layers of compacted gravel, crushed stone, rubble, and carefully leveled bedding materials. These were not random construction fills. Each layer appears intentionally selected to improve drainage while distributing structural loads over a wider surface area. What remains unknown is how Roman surveyors determined the required thickness of each layer without mathematical models describing settlement, bearing capacity, or differential compression. No surviving Roman text explained such calculations, and none of the construction drawings have survived. The result is even more astonishing because large portions of the Forum have experienced surprisingly limited differential settlement despite centuries of freeze-thaw cycles, groundwater fluctuations, agricultural activity, medieval construction, and modern urban development. Recent geotechnical studies at comparable Roman foundations suggest that compacted granular layers can significantly reduce localized deformation by redistributing vertical loads before they reach compressible clay. However, reproducing Bagacum's performance remains difficult because the original construction sequence cannot be reconstructed with complete certainty. Archaeologists know the materials that were used, but not the precise order, moisture content during compaction, tamping methods, or quality control procedures followed by Roman builders. Those missing details may represent the difference between a foundation surviving centuries and one failing within decades. Above these hidden foundations stood one of the largest cryptoporticus systems in Roman Gaul. Long underground galleries surrounded sections of the Forum, supporting enormous loads while simultaneously creating protected storage areas and stabilizing the terrain above. Massive masonry vaults transferred weight through continuous arches into carefully prepared foundations, rather than concentrating pressure beneath isolated walls. Structural engineers studying surviving Roman vaults have repeatedly noted how effectively compressive forces travel through these arches, reducing stress concentrations that normally accelerate settlement in weak soils. Even today, many portions preserve their original geometry with minimal distortion, suggesting that Roman builders intuitively understood load paths at a remarkably sophisticated level despite lacking modern structural analysis. Water management introduces another layer of engineering that remains only partially understood. Heavy rainfall poses a serious threat to clay-rich terrain because excess moisture weakens bearing capacity while increasing seasonal ground movement. Excavations throughout Bagacum have uncovered extensive drainage channels, underground conduits, stone-lined sewers, and carefully graded streets directing runoff away from monumental buildings. Several surviving drains still maintain gradients sufficient for gravity-driven flow after nearly 2,000 years. Modern surveys indicate that some Roman drainage systems operated with slopes measured in only a few millimeters per meter, requiring exceptional precision over considerable distances. How surveyors consistently achieve these gradients using instruments such as the asterisk, chroma, chorobates, and simple leveling devices continues to fascinate historians of engineering. The city's remarkable stability becomes even more surprising when considering the enormous quantities of the building stone involved. Much of the limestone used in Bagacum originated from regional quarries rather than the immediate construction site. Individual architectural blocks weighed several tons, demanding coordinated quarrying, transport, lifting, and placement across terrain, frequently softened by moisture. Archaeological evidence confirms the existence of Roman treadwheel cranes capable of lifting heavy loads, yet the precise logistical organization employed at Bagacum remains speculative because direct construction records have never been discovered. Every accurately positioned block ultimately transferred its weight onto foundations resting above ground that should have been inherently unstable. Precision surveying appears throughout the city's layout. Streets intersect at consistent angles, monumental buildings align with the orthogonal street grid, and the Forum exhibits remarkable geometric regularity across hundreds of meters. Such accuracy required more than careful craftsmanship. It demanded reliable surveying methods capable of maintaining straight alignments over long distances despite changing topography. Roman surveyors undoubtedly relied upon standardized instruments, but the exceptional consistency observed at Bagacum suggests field procedures whose practical sophistication exceeded the surviving written descriptions contained in authors such as Vitruvius. The network of roads converging on Bagacum reflects the same level of technical confidence. Several major Roman highways extended for hundreds of kilometers while maintaining strikingly straight trajectories whenever terrain permitted. These routes crossed forests, wetlands, river valleys, and rolling landscapes with deviations far smaller than one might expect from pre-industrial surveying. Modern satellite imagery vividly illustrates how many of these ancient alignments still define transportation corridors across northern France and Belgium. Establishing such routes required not only directional accuracy, but also continuous evaluation of drainage, soil stability, gradients, and long-term maintenance, indicating an integrated engineering strategy extending far beyond the city itself. In the province of Avila in central Spain, overlooking the Ambles Valley, lies Mesa de Miranda, an Iron Age hill fort whose surviving granite walls continue to raise engineering questions more than 2,000 years after they were built. Hidden among rugged uplands at an elevation of roughly 1,400 meters, this vast settlement appears at first to be another Celtic ruin. Yet behind its weathered stones stands a construction project whose precision, stability, and scale seem unexpectedly advanced for a society working centuries before Roman domination of the Iberian Peninsula. Mesa de Miranda remained largely unknown outside the local region until systematic archaeological excavations began during the 20th century, particularly through the work of Spanish archaeologist Juan Cabreaguilo, and later investigations carried out by the University of Salamanca and regional heritage institutions. Excavations revealed that the site belonged to the Veternes, a Celtic-speaking people occupying Western Iberia between approximately the 5th and 1st centuries BC. Archaeological evidence indicates that the enclosed settlement covered nearly 30 hectares and was protected by almost 3 kilometers of defensive walls, making it one of the largest fortified veteran settlements ever identified. The enormous size of the enclosure immediately presents the first puzzle. Building nearly 3 kilometers of fortification was already an extraordinary undertaking, but the greater mystery lies in how the entire defensive system was planned across an irregular granite plateau. The walls do not simply follow the easiest route around the hill. Instead, they bend with remarkable consistency around natural ridges, cliffs, terraces, and steep slopes while preserving defensive continuity. Even with modern topographic mapping, designing such a layout requires careful surveying because every change in elevation alters sightlines, access routes, and structural loads. Archaeologists have found no evidence of written architectural plans, measuring instruments comparable to Roman surveying equipment, or standardized engineering manuals from the Veternes. Yet the overall geometry suggests that someone possessed a remarkably accurate understanding of terrain long before construction began. The greatest engineering mystery, however, lies within the walls themselves. Mesa de Miranda is built primarily with Cyclopean masonry, a construction technique that relies on massive granite blocks assembled without mortar. Although the term Cyclopean was coined much later by Greek observers who believed only mythical giants could move such stones, the technique appears throughout prehistoric Europe in several independent traditions. At Mesa de Miranda, the walls often measure between 3 and 5 meters thick, while their original height is estimated to have reached 6 to 8 meters in some sectors. Considering their total length, Researchers estimate that tens of thousands of tons of granite were extracted, transported, positioned, and locked together with astonishing accuracy. Unlike later Roman masonry, these stones were rarely cut into regular rectangular blocks. Most preserve much of their natural shape, yet they fit together with surprising efficiency. Modern structural engineers describe this as a self-stabilizing dry stone system, where stability is achieved not by cement but by gravity, friction, and carefully distributed loads. Every irregular surface increases contact with neighboring stones, reducing movement while allowing microscopic adjustments during seasonal expansion and contraction. Instead of behaving like a rigid concrete wall that may crack under stress, the entire structure functions almost as a flexible mechanical assembly capable of absorbing gradual shifts in the ground. This characteristic explains why significant sections remain standing after more than 22 centuries despite repeated freeze-thaw cycles, earthquakes of low to moderate intensity, seasonal erosion, and continuous weathering. Granite itself possesses exceptional compressive strength, often exceeding 100 megapascals depending on mineral composition. But strong stone alone cannot explain the survival of such immense walls. Countless ancient granite structures have collapsed after losing internal stability. Mesa de Miranda did not simply rely on durable material. It relied on a construction philosophy that modern dry stone engineering increasingly recognizes as remarkably sophisticated. The question becomes far more difficult when one considers the practical process of assembly. Every irregular block possesses a unique center of gravity. If positioned incorrectly, even a slight imbalance could destabilize the courses above it. Builders therefore needed to predict how each stone would distribute its weight before lifting it into place. Across nearly 3 kilometers of fortification, that process had to be repeated thousands of times with extraordinary consistency. Experimental archaeology has demonstrated that constructing stable dry stone walls requires experienced masons capable of mentally visualizing 3-dimensional load paths. Mesa de Miranda expands that challenge from individual buildings to an entire defensive landscape. Researchers also remain uncertain about the methods used to transport the granite. Many blocks weigh between 2 and 5 metric tons, with some likely exceeding that range. The nearest granite outcrops provided abundant material, but moving stones of this size uphill across uneven terrain without iron cranes, wheeled construction vehicles, or documented pulley systems demanded immense coordination. Proposed methods include timber rollers, sledges, rope made from plant fibers, teams of oxen and earthen ramps. Each technique works in controlled experiments, yet no direct archaeological evidence identifies which solution was actually employed here. Even more intriguing, some stones occupy locations where steep gradients would have complicated every stage of transport. Equally impressive is the internal structure of the fortifications. Excavated sections reveal that the walls were not simple piles of stone. Large facing blocks enclosed a carefully packed interior core consisting of smaller stones and rubble. This composite design distributed pressure evenly across the wall, while minimizing empty spaces that could weaken the structure. Similar engineering principles appear centuries later in Roman fortifications, but the Vetans developed their own version independently. Such internal packing also improved drainage by allowing rainwater to filter gradually through the wall, instead of accumulating behind it, reducing hydrostatic pressure that commonly destroys ancient masonry. The placement of gateways demonstrates another level of strategic thinking. Rather than opening directly toward approaching visitors, entrances forced movement through narrow-angle passages where attackers would repeatedly expose their unshielded sides. Modern military historians describe comparable arrangements as creating controlled killing zones because defenders positioned above could attack invaders trapped within confined approaches. The remarkable aspect is not simply the existence of defensive gateways, but their integration with the surrounding topography. Natural cliffs, steep slopes, and projecting walls combine into a single defensive system that appears carefully modelled around expected enemy movement rather than imposed upon the landscape afterward. One feature especially associated with Veton settlements further strengthens this impression. Around vulnerable sectors, archaeologists uncovered extensive fields of upright pointed stones, known by the French term chevaux de frise. Hundreds of granite spikes projected from the ground at regular angles, forming an obstacle designed to disrupt advancing infantry and, more importantly, mounted cavalry. Similar defensive barriers appeared much later in medieval Europe. Yet, the Vetoners implemented the concept centuries earlier. Their distribution was highly selective. Instead of surrounding the entire settlement, these stone fields protected only those sectors where approaching forces could realistically assemble, revealing a surprisingly detailed understanding of battlefield geometry. Modern technologies have added new layers to the investigation instead of closing the debate. High-resolution aerial photography, LiDAR surveys, photogrammetry, and digital terrain modeling reveal subtle geometric relationships invisible from ground level. These studies show that builders repeatedly selected the most structurally advantageous positions along natural bedrock, rather than following visually symmetrical layouts. The fortifications appear optimized to exploit geological stability while minimizing unnecessary construction volume, an approach entirely consistent with principles used in modern geotechnical engineering. Whether this knowledge resulted from generations of accumulated empirical observation or from specialized builders transmitting highly developed construction traditions remains unknown. Beneath the limestone plateau of present-day El Burgo de Osma in Spain lies Uxamar Gaela, a Roman city whose greatest monument was never built above the skyline. Its most astonishing achievement disappeared inside solid rock, where engineers nearly 2,000 years ago carved an underground hydraulic system so precise that archaeologists are still debating how it was surveyed and executed without modern instruments. The first traces of ancient Uxamar attracted scholarly attention during the 18th century, but systematic archaeological excavations throughout the 20th century gradually revealed an extensive Roman municipality occupying more than 28 hectares. Beneath its streets appeared an unexpected network of tunnels, cisterns, and water conduits cut directly into the limestone bedrock, exposing an engineering project far more ambitious than anyone had imagined from the surviving ruins alone. The greatest mystery begins with a question that should never have needed an answer. Why establish a flourishing Roman city on a dry limestone plateau where dependable surface water was scarce? The obvious solution would have been to settle closer to the Duero River, yet Uxamar stood several kilometers away and nearly 100 meters above the valley floor. Rather than moving the city toward water, Roman engineers forced water to come to the city. Everything discovered since suggests that this decision demanded an extraordinary level of geological understanding and hydraulic planning. Unlike masonry aqueducts stretching across valleys, much of Uxamar's water system vanished inside the mountain itself. Archaeological investigations have documented long underground galleries excavated through compact limestone, linking springs, reservoirs, and distribution points across the urban centre. Some galleries extend for several hundred meters, while maintaining gradients so gentle that water continued flowing only under gravity. Modern hydraulic engineering recognizes that even minor deviations in slope can dramatically affect flow velocity. Excessive inclination causes destructive erosion and turbulence, while insufficient inclination produces stagnation and sediment accumulation. Measurements from Roman aqueducts across the empire commonly reveal gradients between roughly 1 and 3 meters per kilometer, and evidence from Uxama indicates its underground conduits followed similarly demanding tolerances despite disappearing entirely through solid rock. That precision creates the real mystery. Roman surveyors certainly possessed instruments such as the chorobates, chroma and dioptra, yet none were designed to see through mountains. Once excavation disappeared beneath the surface, maintaining a nearly constant elevation required knowing exactly where the tunnel should emerge hundreds of meters later. There are no surviving construction drawings, no measurement records, and no written explanation describing how Uxama's engineers transferred reference levels through an invisible underground route. Every meter carved into bedrock increased the consequences of even a slight surveying error. A deviation of only a few centimeters in elevation could eventually leave an entire conduit incapable of delivering water to its destination. Even more remarkable is the internal consistency of these galleries. Their cross-sections remain surprisingly regular despite passing through natural variations in limestone hardness. Tool marks preserved on several walls reveal systematic excavation rather than irregular enlargement. Instead of following fractures wherever they appeared, workers repeatedly maintained plan dimensions, suggesting that geometry mattered as much as excavation speed. This indicates careful coordination between surveying teams and stonecutters working in confined underground spaces illuminated only by oil lamps. Ventilation introduces another engineering puzzle. Long tunnels rapidly become dangerous because oxygen decreases while smoke from lamps accumulates. Excavations have identified vertical shafts opening from the galleries toward the surface. These shafts almost certainly removed excavated debris and circulated fresh air, yet their spacing also appears remarkably deliberate. Engineers seem to have anticipated the entire underground route before excavation advanced very far, positioning access shafts where they would remain useful throughout construction, rather than responding only after problems emerged. Such planning implies a surprisingly complete understanding of the unseen geology beneath the plateau. Some researchers have suggested that different excavation teams worked simultaneously from separate entrances. If true, they eventually had to meet underground with extraordinary accuracy. Similar Roman mining operations elsewhere demonstrate that opposing tunnels could intersect with errors measured only in decimeters after hundreds of meters of excavation. Whether every gallery at Uxama employed this technique remains debated, but the surviving geometry strongly suggests that Roman engineers possessed surveying methods capable of achieving precision still impressive by modern archaeological standards. The underground conduits ultimately fed one of the most sophisticated systems of rock-cut reservoirs in Roman Hispania. Instead of constructing freestanding tanks from masonry blocks, builders hollowed enormous chambers directly into limestone. Several cisterns descend approximately 8 to 10 meters below the surface, and together stored hundreds of cubic meters of water, providing reserves capable of sustaining the population through seasonal fluctuations. Excavating such volumes without destabilizing surrounding rock required understanding natural stress distribution long before structural geology became a science. Walls remain remarkably straight, corners unexpectedly sharp and floors comparatively level despite being carved entirely by hand. Creating a cavity is only half the challenge, preventing it from leaking is considerably harder. The interiors were coated with opus signinum, a waterproof mortar composed primarily of lime mixed with crushed ceramic fragments. Laboratory analyses of Roman hydraulic mortars elsewhere in the Mediterranean have demonstrated that reactions between lime and ceramic particles generated durable calcium silicate compounds capable of resisting continuous moisture. In several Uxama reservoirs, Portions of this waterproof lining remain attached after nearly 2 millennia, despite repeated cycles of saturation, evaporation, and seasonal temperature changes. Modern conservation specialists continue studying why certain Roman mortar formulations retain their integrity for centuries, while many later historical mortars deteriorated far more rapidly. Once stored, the water had to reach every important district without mechanical assistance. Excavations indicate that baths, fountains, and residential quarters received water through an interconnected distribution network operating entirely by gravity. This required balancing storage capacity, conduit diameter, hydraulic pressure, and consumption rates across the city. The remarkable aspect is not simply that water flowed, but that it apparently flowed reliably enough to sustain a substantial urban population on terrain that initially appears unsuitable for permanent settlement. The surrounding landscape adds another layer to the puzzle. Uxama occupied elevated defensive ground, an obvious military advantage but a hydraulic disadvantage. Engineers therefore had to identify springs capable of supplying sufficient discharge throughout changing seasons before investing enormous labor into excavation. Geological surveys show that the plateau contains permeable limestone intersected by water-bearing layers, yet recognizing exactly where those resources could be exploited without modern hydrogeology required generations of accumulated practical knowledge that remains only partially understood today. Evidence preserved on the rock surfaces also hints at a disciplined construction process. Parallel chisel marks reveal repetitive working sequences rather than random excavation. Individual blows appear organized into systematic patterns that maximized efficiency while minimizing uncontrolled fracturing. Considering that thousands of cubic meters of limestone were removed, the project demanded careful logistics involving lighting, ventilation, debris removal, tool maintenance, and workforce coordination deep underground. Surprisingly, little archaeological evidence has survived to explain how such an operation was organized on a daily basis. Equally intriguing is what has not been found. Removing thousands of cubic meters of stone should have produced enormous spoil heaps surrounding the city, yet no corresponding deposits have been conclusively identified. Archaeologists suspect much of the excavated limestone was recycled into walls, streets, and public buildings, but reconstructing the complete movement of this material has proven difficult. If extensive reuse occurred, it would reveal a remarkably efficient construction economy in which excavation waste immediately became architectural resource. Tucked away within the foothills of the Central Pyrenees in Huesca province, northeastern Spain, the forgotten Roman city of La Tolosa preserves an engineering puzzle that still resists complete explanation. The ruins remained buried for centuries until scattered inscriptions and architectural fragments attracted scholarly attention during the 19th century, while systematic archaeological excavations beginning in the late 20th century gradually revealed an exceptionally well-preserved Roman municipium occupied mainly between the 1st and 3rd centuries AD. Excavations uncovered the forum, curia, baths, residential quarters, drainage systems, and hydraulic infrastructure, offering one of the clearest archaeological windows into how a relatively small provincial Roman city actually functioned. What immediately separates La Tolosa from countless other Roman settlements is not its size, but its location. Unlike cities established across broad plains, La Tolosa occupied a naturally uneven hillside overlooking the Acera River Valley. The terrain rises and falls across limestone ridges with irregular gradients, creating a landscape that should have complicated almost every aspect of urban planning. Yet, instead of adapting individual buildings independently, Roman engineers managed to integrate streets, public monuments, drainage channels, and water distribution into a remarkably coherent hydraulic network. The greatest unanswered question is not whether they possess sufficient engineering knowledge, they clearly did, but exactly how they achieved such precision using surveying instruments that appear primitive by modern standards. Every Roman city depended on water, yet supplying water to a settlement built across sloping terrain presented an engineering challenge far beyond simply transporting it from a nearby spring. Gravity was both an ally and an enemy. If the gradient became too steep, flowing water would rapidly erode channels, damage masonry, and generate destructive hydraulic pressure. If the slope became too gentle, suspended sediments would accumulate, biological growth would increase, and flow could eventually stagnate. Modern hydraulic engineers routinely solve these problems with laser surveying, digital elevation models, pressure calculations, and computer simulations. Roman engineers possessed none of those technologies, yet archaeological evidence at Labitolosa suggests they maintained gradients sufficiently controlled for an urban water system to operate reliably for generations. Although the complete water supply network has never been recovered, archaeologists have identified portions of stone conduits, reservoirs, distribution structures, and drainage channels, indicating that water entered the city from higher ground before descending naturally through carefully managed elevation changes. The missing sections remain one of the site's greatest mysteries. No surviving aqueduct spans the surrounding landscape, and the original spring feeding the network has never been identified with certainty. This means researchers still cannot reconstruct the entire hydraulic circuit from source to consumer. The missing evidence has created an unusual situation in which the functioning system is visible inside the city, while its essential beginning remains hidden somewhere beyond the excavated area. The precision required becomes even more remarkable when considering Roman surveying methods. Ancient authors describe instruments such as the chorobates, essentially a long leveling bench using water and plumb lines, and the groma, designed primarily for establishing straight lines and right angles. Neither instrument appears capable, at least on paper, of maintaining sub-percent gradients across rugged hillsides over extended distances with the consistency visible in many Roman hydraulic works. Experimental archaeology has demonstrated that the chorobates could achieve surprisingly accurate leveling under favorable conditions, yet reproducing an entire municipal water network through broken terrain would have demanded thousands of individual measurements accumulated over considerable distances. Every tiny surveying error would compound until water either accelerated uncontrollably or stopped flowing altogether. The operational success implied by Labitolosa suggests a practical surveying expertise exceeding what surviving technical descriptions alone can explain. Inside the city, water appears to have been managed rather than merely transported. Distribution required balancing flow between public buildings, private residences, fountains, baths, and drainage infrastructure without exhausting supply during seasonal fluctuations. Roman hydraulic engineering elsewhere often relied on settling tanks that reduced suspended sediment before water entered urban pipelines, while overflow structures regulated pressure during periods of high discharge. Although only fragments survive at Labitolosa, the arrangement strongly suggests comparable hydraulic principles were employed. Exactly how local engineers calculated capacity without modern hydrological equations remains unknown, since no construction manuals or engineering records specific to the city have survived. The public baths reveal another layer of technical sophistication hidden behind apparently ordinary stone walls. Heating such a complex required continuous coordination between fuel consumption, airflow, structural stability, and temperature distribution. Beneath the floors stood dense grids of small brick pillars supporting suspended pavements through which hot gases circulated after leaving the furnace. Hollow ceramic wall flues continued carrying heated air upward before it escaped through roof vents, transforming the entire building into an enormous convection system. Archaeological remains demonstrate that the hypocaust functioned efficiently enough to create separate cold, warm, and hot rooms while avoiding catastrophic overheating of the masonry itself. Even today, thermal engineers recognize how difficult it is to maintain relatively even heating across large enclosed spaces without mechanical circulation. Roman builders achieved this using nothing beyond carefully designed geometry and natural airflow. Equally intriguing is the durability of the suspended floors. Continuous thermal expansion and contraction typically produce fractures in masonry over time, particularly when repeated daily for decades. Yet significant portions of the Bath complex survived centuries before eventual collapse through abandonment rather than immediate structural failure. Researchers continue investigating how Roman mortars, brick dimensions, and support spacing interacted to absorb mechanical stress without compromising stability. Laboratory analysis of Roman lime mortars elsewhere has shown ongoing mineral reactions capable of sealing microscopic cracks long after construction. But the precise behavior of materials used specifically at Labitolosa remains only partially understood. Once water completed its journey through homes and public buildings, another engineering challenge began. Wastewater needed removal before it contaminated streets or foundations. Excavated drains beneath Labitolosa display gradients carefully calibrated to maintain flow while minimizing erosion of channel walls. Modern sanitary engineering refers to this balance as self-cleansing velocity, a condition in which moving water carries sediment away before deposition occurs. Calculating such behavior today requires hydraulic equations developed over many centuries, yet Roman drainage systems repeatedly demonstrate remarkably effective practical solutions. Whether their success resulted from empirical observation accumulated across generations or mathematical understanding now lost remains an open question. Excavations of the Curia, the municipal council building, illustrate that sophistication extended below ground. Foundations consist of carefully arranged stone blocks distributing structural loads across naturally variable terrain. Differential settlement appears surprisingly limited considering the geological conditions, suggesting Roman builders understood local soil behavior far better than written evidence indicates. Since no geotechnical documentation survives, archaeologists can only infer construction methods from the finished structures themselves. On a narrow Atlantic headland overlooking the Bay of Biscay in Fazuro, Galicia, northwestern Spain, the remains of a small Iron Age settlement challenge one of archaeology's oldest assumptions, that advanced engineering belonged only to the great civilizations of the ancient world. Hidden above cliffs battered by relentless ocean storms, Castro de Fazuro preserves evidence of builders who mastered drainage, structural planning, and environmental adaptation, with techniques whose underlying design principles are still only partly understood. The site remained unnoticed by modern archaeology until the early 20th century, but systematic excavations carried out from the 1960s onward uncovered an exceptionally well-preserved coastal castro, occupied between approximately the 1st century BC and the 2nd century AD. Unlike most fortified settlements of northwestern Iberia, many of which survive only as buried foundations, Castro de Fazuro exposed complete house plans, paved streets, workshops, drainage features, and defensive structures, providing an unusually detailed picture of daily engineering during the transition from indigenous Castro culture to Roman influence. Archaeological investigations conducted by the Junta de Galicia indicate that roughly 9 architectural structures have been documented within an excavated area of only about 400 square meters, revealing a surprisingly organized settlement despite its modest size. The first feature that immediately separates Castro de Fazuro from countless other Iron Age villages is not its walls or its houses, but the remarkable way it controls water. The settlement occupies one of the least forgiving locations imaginable for permanent habitation. Galicia receives between 1,000 and 2,000 millimeters of rainfall annually, depending on elevation, while Atlantic storms repeatedly drive rain horizontally across the exposed cliffs. Salt spray, strong winds, and continuous moisture normally accelerate structural decay, yet the excavated buildings show clear evidence that standing water inside domestic spaces was systematically prevented. Rather than relying on underground sewer systems like those developed in Roman cities, the builders transformed the entire settlement itself into a gravity-powered hydraulic network. Individual houses were intentionally raised slightly above adjacent open spaces, creating subtle elevation differences that are barely noticeable today but sufficient to direct runoff away from living areas. Stone-paved floors were laid with carefully calculated gradients, allowing rainwater to travel naturally toward exterior circulation zones before leaving the settlement altogether. Narrow gaps between walls acted as controlled drainage passages, while exterior courtyards functioned as intermediate collection surfaces instead of allowing water to accumulate against foundations. None of these elements appears accidental. Each building contributes to a larger hydraulic pattern that only becomes visible when the settlement is viewed as an integrated engineering system rather than as isolated houses. What makes this achievement particularly difficult to explain is the apparent precision with which these gradients were established. Modern engineers accomplish comparable work using laser levels, surveying instruments, and mathematical calculations. The inhabitants of Castro de Fazuro possess none of these technologies. No measuring devices, construction plans, or written architectural manuals have ever been recovered from the site. Yet the surviving foundations indicate that builders repeatedly reproduced effective drainage geometry across multiple structures. Even an error of only a few centimeters in floor elevation could have caused water to flow back into houses during heavy Atlantic rainfall. But archaeological evidence suggests the system performed successfully for generations. Whether these builders relied upon sophisticated empirical surveying techniques, inherited construction traditions refined over centuries, or some now lost method of establishing consistent gradients remains unknown. Equally intriguing is the choice of construction material. Most monumental architecture across the Roman world depended heavily upon massive limestone or granite blocks. Yet Castro de Fazuro was built largely with locally available slate. At first glance, this appears entirely practical, but slate presents engineering difficulties of its own. Because it naturally splits along thin planes, improperly oriented blocks can fracture under repeated loading or weather exposure. The walls surviving at Fazuro demonstrate that builders consistently place the stone in orientations, maximizing compressive strength while minimizing delamination. Such knowledge implies a detailed practical understanding of rock mechanics acquired without geological science. Archaeologists still debate whether this expertise developed through generations of accumulated experience or represented standardized construction practices transmitted among specialized builders throughout the Castro culture. The organization of the settlement itself also reveals planning far beyond what its modest dimensions might suggest. Excavated structures share walls, reuse earlier foundations, and maintain orderly circulation routes, despite being constructed during different occupational phases. Instead of expanding randomly as families increased, the community appears to have followed spatial rules that balance domestic needs, workshops, access routes, and drainage simultaneously. This level of coordinated planning resembles principles seen in far larger Roman settlements, yet Castro de Fazuro never reached urban scale. The settlement demonstrates that sophisticated planning does not necessarily require monumental size. Evidence of metallurgy introduces another engineering question. Excavations identified a workshop containing slag deposits, combustion installations, and stone-built working areas associated with high-temperature metal production. Producing iron requires sustained temperatures exceeding approximately 1,100 degrees Celsius, while efficient bloomery furnaces depend upon carefully controlled airflow. Locating such activity immediately beside the Atlantic coast seems counterintuitive because humid marine air and salt-laden winds generally complicate combustion and accelerate corrosion. Some researchers have suggested that the prevailing coastal winds may actually have provided a natural source of forced ventilation, reducing the labor required to operate bellows continuously. Although no surviving furnace allows this hypothesis to be tested directly, the possibility that local wind conditions became an intentional component of metallurgical engineering remains an intriguing unanswered question. Defensive planning demonstrates the same philosophy. Castro de Fazuro occupies a rocky promontory where steep cliffs naturally protect most approaches. Rather than investing enormous labor constructing continuous fortification walls around the entire settlement, builders concentrated defensive works only where the terrain remained vulnerable. Earthworks and walls strengthened the accessible landward side, while the Atlantic itself became an integral component of the defensive system. Modern military engineers describe this approach as force multiplication through terrain exploitation, yet its principles were clearly understood here nearly 2,000 years ago. Every meter of unnecessary wall represented labor saved without reducing security. Perhaps the most overlooked engineering mystery concerns survival itself. The Atlantic coastline of Galicia experiences continuous erosion driven by waves, rainfall, salt crystallization, and seasonal temperature fluctuations. Geological studies estimate that marine cliff retreat, although highly variable, gradually removes sections of coastline over centuries. Despite occupying the edge of an exposed headland, substantial portions of Castro de Fazuro remain remarkably intact after nearly 2 millennia. Some sectors have undoubtedly disappeared into the sea, yet the preserved core suggests that the original builders deliberately selected one of the most stable bedrock platforms available. Whether this choice resulted from careful observation of geological stability over generations or from practical trial and error can no longer be determined, but the accuracy of that decision continues to protect the settlement today. Located among the limestone hills near Alcañiz in the province of Teruel, northeastern Spain, El Palau appears at first glance to be little more than a weathered hilltop scattered with ancient stones. Yet beneath those ruins lies one of the most sophisticated Iberian settlements ever uncovered, a place where engineers solved problems of water, construction and urban planning long before Roman administration reached the region. Archaeologists first identified the archaeological importance of El Palau during surveys in the 19th century, but systematic excavations carried out throughout the 20th century and continuing into the present have revealed a settlement occupied from roughly the 7th or 6th century BCE until the early 2nd century CE. Covering more than 5 hectares, the city expanded through the Iberian and Roman Republican periods into one of the principal political and economic centers of Bajo Aragon, despite standing on a rocky hill where permanent springs are entirely absent. That contradiction immediately raises the central mystery. How could a settlement of this scale survive for centuries in a place that seemingly lacked the most basic requirement for urban life? The answer begins with a remarkable hydraulic system buried beneath the streets. excavations uncovered a monumental stone-built cistern designed to capture, filter, store and distribute rainwater throughout the settlement. Although reservoirs are not unusual in Mediterranean archaeology, the engineering demonstrated at El Palau is unusually sophisticated for an Iberian community. The builders selected a naturally elevated limestone platform, then reshaped the surrounding terrain to direct seasonal runoff toward carefully constructed collection points. The interior walls of the reservoir were coated with hydraulic mortar capable of resisting continuous moisture, while the floor was graded with remarkable precision to prevent stagnant water from accumulating in isolated depressions. Even after more than 2,000 years of erosion, archaeologists can still identify waterproof surfaces that remain surprisingly intact, demonstrating an understanding of construction materials far beyond what many would expect from an Iron Age society. What remains unexplained is not that the inhabitants collected rainwater, but how accurately they calculated the entire hydraulic network without modern surveying equipment. A gradient only slightly too steep would have accelerated erosion inside the channels, while one too shallow would have allowed sediment to accumulate and block the system. Yet surviving sections indicate remarkably consistent slopes over considerable distances. Researchers believe much of the original drainage network has disappeared beneath later occupation layers, making complete reconstruction impossible. As a result, the full design can only be inferred from scattered architectural fragments, rather than observed directly. This missing evidence leaves one of El Palau's greatest engineering achievements only partially understood. Even more remarkable is the possibility that the city itself was planned around this hydraulic infrastructure from its earliest expansion. Instead of constructing houses first and solving water shortages later, archaeological evidence suggests the opposite sequence may have occurred. Streets appear to converge towards strategic drainage routes, while public spaces occupy positions that would have simplified runoff collection during seasonal storms. Such integration implies an urban planning strategy that considered topography, rainfall, storage capacity, and future population growth simultaneously. For an Iberian settlement centuries before full Roman municipal organization, this level of coordinated planning remains exceptional. The hill chosen for El Palau only deepens the puzzle. Limestone bedrock rarely provides generous building platforms, forcing ancient builders to carve terraces directly into uneven slopes before any major construction could begin. Massive retaining walls were erected to stabilize these artificial levels, preventing landslides during periods of heavy rainfall. Some foundations rest directly against natural rock faces, while others bridge abrupt changes in elevation with carefully fitted masonry. Modern engineers recognize that poorly designed terrace systems eventually fail as soil pressure increases over time, yet many of El Palau's retaining structures continue to stand after more than 20 centuries despite repeated freeze-thaw cycles, characteristic of the continental climate of Aragon. The precise methods used to stabilize these foundations remain uncertain because the organic construction materials that may once have reinforced them have long since disappeared. As excavation expanded across the site, archaeologists realized the settlement was far more organized than previously imagined. Residential districts, industrial workshops, storage facilities, defensive sectors, and circulation routes occupy distinct zones rather than developing randomly across the hilltop. Olive oil production installations have been identified alongside storage buildings capable of preserving agricultural products for extended periods. Such infrastructure implies not merely local consumption but regional redistribution. El Palau likely functioned as an administrative center, controlling trade routes linking the Ebro Basin with inland Iberia. Yet no written administrative archive survives to explain how resources were managed, taxed, or distributed. The physical evidence reveals a remarkably efficient economic system, while the documents that could explain its operation have vanished completely. The defensive design reveals another layer of engineering ingenuity. Unlike many fortified settlements that relied on continuous monumental walls, El Palau exploited natural geography to reduce the amount of masonry required. Steep escarpments formed much of the defensive perimeter, while artificial walls reinforced only the most vulnerable approaches. Towers were positioned where attackers would be forced to slow during ascent, creating overlapping fields of observation rather than depending on sheer wall thickness. Archaeologists have also identified evidence that certain access routes change function over time, evolving from ordinary roads into controlled defensive corridors as political instability increased during the late Iron Age. This flexibility suggests that military planning evolved alongside the settlement instead of remaining fixed from its foundation. One of the site's most intriguing discoveries consists of finely carved stone sculptures, including equestrian figures and anthropomorphic fragments demonstrating artistic abilities usually associated with much larger urban centres. Transporting the necessary limestone blocks uphill would itself have required considerable logistical organisation. Since no quarry directly adjacent to the settlement has been identified with certainty, researchers continue investigating where these stones originated and how they were moved across difficult terrain without advanced lifting machinery. Similar questions surround the production of large architectural blocks incorporated into terraces and public buildings, whose dimensions exceed what small household labour groups could easily manipulate. Perhaps the greatest historical mystery is that El Palau may correspond to the ancient city known as Osicerda, a settlement mentioned by the Roman author Pliny the Elder and possibly represented on Iberian coinage bearing the inscription Usucerte. If this identification proves correct, then El Palau was not merely an isolated hill fort but a politically significant urban centre, recognised throughout northeastern Hispania. Yet, despite its apparent importance, almost no contemporary written descriptions survive. The city expanded, prospered, developed advanced hydraulic engineering, supported specialised industries, and participated in regional commerce before gradually disappearing from historical memory with astonishing completeness. Archaeology has recovered streets, reservoirs, workshops, sculptures, and fortifications, but the voices of the people who designed them remain silent. Labranda, located approximately 14 kilometers northeast of the ancient city of Milasa in the forested mountains of southwestern Turkey, is one of the most enigmatic sacred complexes of the ancient Mediterranean. Rising nearly 700 meters above sea level on the rugged slopes of the Latmus Mountains, the sanctuary occupies a location that seems remarkably difficult for large-scale construction. When archaeologists first began systematically studying the site in the 19th and 20th centuries, they expected to find the remains of a typical Greek religious centre. Instead, they uncovered evidence of an engineering achievement that continues to raise difficult questions today. Long before modern roads, cranes, surveying instruments, and geological analysis, ancient builders somehow transformed a steep mountainside into a monumental sanctuary capable of hosting thousands of pilgrims, transporting enormous quantities of stone, managing water in a rocky environment, and surviving earthquakes for more than 2,000 years. Excavations reveal that Labranda reached its greatest importance during the 4th century BCE under the Hecatomnid rulers of Korea, particularly Mausolus and Idrieus. Archaeologists uncovered temples, banquet halls, monumental staircases, retaining walls, water systems, defensive structures, and a sacred road connecting the sanctuary to Milasa. What emerged was not merely a religious site, but an integrated mountain infrastructure project. The deeper researchers investigated, the more difficult it became to explain how ancient engineers achieved such precision in terrain that even modern construction crews would consider challenging. The first mystery begins with the mountain itself. Most major ceremonial centers of the ancient world were built on relatively accessible terrain. The great temples of Egypt stood along the Nile. Mesopotamian cities occupied river plains. Even many Greek sanctuaries were established in locations where building materials and labor could be transported with relative ease. Labranda was different. Every block of stone, every architectural element, every tool, and every construction material had to be moved uphill through steep terrain. The sanctuary contains numerous granite blocks weighing several tons each. Modern engineers estimate that moving such loads over mountain routes without mechanized transport would require careful coordination, specialized hauling systems, and significant manpower. Researchers believe the builders used sledges, rollers, ropes, and teams of workers or animals. Yet the scale of the operation remains difficult to reconstruct. The sacred complex expanded over decades, requiring thousands of tons of material. Unlike sites connected to rivers or coastal ports, Labranda offered no convenient transportation corridor. The challenge becomes even more remarkable when compared with famous mountain sites such as Machu Picchu. Although Machu Picchu sits at a higher elevation, many of its stones were quarried nearby. At Labranda, evidence suggests that large quantities of stone and construction materials were transported considerable distances before reaching the sanctuary itself. The mystery deepens with the sacred way linking Labranda to Milisa. Archaeological surveys have identified portions of this ancient road extending approximately 14 kilometers through rugged, mountainous terrain. The route was not a simple trail. It was an engineered transportation corridor. Sections reveal retaining walls, paving stones, drainage systems, and carefully controlled gradients. Modern road engineers understand that maintaining a practical slope is essential for moving heavy loads efficiently. Too steep and transport becomes dangerous. Too shallow and construction costs increase dramatically. What fascinates researchers is the apparent optimization of the route. Ancient surveyors, lacking satellite imagery, topographic maps, laser scanners, or GPS technology, somehow selected a path that balanced distance, elevation gain, stability, and accessibility. Similar challenges confronted Roman road builders centuries later. Yet portions of the sacred way demonstrate a level of terrain adaptation that continues to impress modern archaeologists. Some sections remain recognizable after more than 23 centuries of erosion, earthquakes, and environmental change. The mountain terraces of Labranda present another engineering puzzle. The sanctuary was not built on a naturally flat surface. Instead, the builders transformed steep slopes into a sequence of artificial platforms capable of supporting large stone structures. To achieve this, they constructed massive retaining walls designed to resist gravitational pressure from both the hillside and the buildings above. Modern geotechnical engineers know that retaining walls are among the most challenging structures to design because failure can trigger catastrophic landslides. Even small errors in drainage or load distribution may lead to collapse. Yet many of Labranda's terraces remain remarkably stable today. The builders appear to have understood how water affects soil pressure, how loads transfer through foundations, and how bedrock can be incorporated into structural support systems. The precise methods they used remain uncertain because almost no technical documentation survives. Water management introduces another layer of mystery. Labranda sits on a mountain where large permanent water sources are limited. Nevertheless, historical evidence suggests that the sanctuary hosted major religious festivals attracting substantial crowds. Providing water for hundreds or even thousands of visitors would have been essential. Archaeologists have discovered reservoirs, channels, collection systems, and hydraulic features indicating sophisticated water management. The challenge is considerable. In Mediterranean climates, annual rainfall is concentrated in specific seasons, while summers can be extremely dry. Successful operation required storing enough water to bridge prolonged dry periods. Similar water management achievements are known from Petra in Jordan and Masada in Israel, where ancient engineers captured seasonal rainfall and distributed it efficiently. Labranda appears to belong within this tradition of hydraulic ingenuity. However, portions of the original system remain poorly understood, leaving unanswered questions about its total storage capacity and operational efficiency. Perhaps the most intriguing mystery concerns the sanctuary's long-term survival in one of the most seismically active regions of the Mediterranean. Western Anatolia sits near multiple fault systems that have generated destructive earthquakes throughout recorded history. Numerous ancient cities in the region suffered repeated structural damage or complete destruction, yet significant portions of Labranda endured. Modern structural analysis suggests that the builders deliberately anchored many constructions directly onto bedrock. This strategy reduces differential settlement and improves resistance to seismic forces. Some retaining walls exhibit characteristics that allow slight movement without catastrophic failure, a principle echoed in certain earthquake-resistant techniques observed at Inca sites in Peru. While Labranda does not display the same polygonal masonry seen at Sacsayhuaman, both sites reveal an apparent understanding that rigid structures often fail under seismic stress, whereas controlled flexibility enhances survival. The architecture itself raises questions about ancient surveying capabilities. Buildings across the sanctuary demonstrate consistent alignments despite the irregular terrain. Staircases connect terraces with remarkable precision. Monumental structures maintain geometric relationships that required careful planning before construction began. Achieving such coordination on a mountain slope is far more difficult than on level ground. Modern surveyors would rely on total stations, digital elevation models, and advanced measuring equipment. Ancient builders relied on ropes, sighting instruments, geometry, and accumulated practical knowledge. Some researchers argue that ancient surveying skills have been systematically underestimated. Across the Mediterranean, sites such as Priena, Ephesus, and Pergamon demonstrate impressive urban planning. Yet Labranda presents a unique challenge because every measurement had to be adapted to a complex natural landscape rather than imposed upon a flat surface. The sanctuary appears less like a collection of independent buildings and more like a single integrated design extending across the mountainside. The influence of multiple civilizations further complicates the mystery. Labranda occupied a cultural crossroads between indigenous Carian traditions, Greek architectural principles, and Persian political influence. The sanctuary's engineering solutions may represent a fusion of knowledge from different worlds. Rather than emerging from a single technological tradition, the site may preserve centuries of accumulated experimentation, adaptation, and innovation. Unfortunately, while the stone structures remain, the manuals, calculations, and engineering instructions have disappeared. Northern Greece. At the edge of a vast ancient marshland beneath the shadow of the Pangion Mountains lie the ruins of Philippi. For more than 15 centuries, this city endured earthquakes, floods, invasions, and environmental change. Yet the greatest mystery is not why it disappeared. The greatest mystery is how it existed there at all. Although travelers had known about the ruins for centuries, systematic archaeological excavations began in the early 20th century. Beneath layers of Byzantine churches, Roman forums, theatres, roads, and fortifications, Archaeologists uncovered evidence of a city continuously occupied from the 4th century BCE until the late Byzantine era. What emerged was not merely an ancient settlement, but a technological puzzle stretching across more than 1,500 years of history. The first mystery begins with geography. Philippi was founded around 356 BCE by Philip II of Macedon. The location was strategically valuable because it controlled access between Europe and Asia through a narrow corridor later crossed by the famous Via Egnatia, one of the most important Roman roads ever constructed. However, from an engineering perspective, the site was deeply problematic. Ancient Philippi stood beside extensive wetlands fed by mountain runoff and seasonal flooding. Geological studies indicate that large portions of the surrounding plain consisted of alluvial sediments, silts, and waterlogged soils. Modern engineers generally avoid placing massive stone structures on such unstable ground without extensive foundation work. Soft sediments compress under weight, causing differential settlement, wall cracking, and structural failure. Yet Philippi developed into one of the most important cities in Macedonia. The puzzle becomes more remarkable when examining the city's longevity. While many ancient settlements built on difficult terrain survived only a few centuries before abandonment or collapse, Philippi remained active for over 1,500 years. During that period, it hosted Macedonian rulers, Roman colonists, early Christian communities, and Byzantine administrators. Archaeological excavations reveal evidence of extensive earthworks and drainage systems beneath major construction zones. Ancient builders appear to have manipulated water flow across the landscape, creating stable zones for urban development. However, researchers still debate the full scale of these interventions. Much of the ancient hydraulic infrastructure remains buried beneath sediments deposited over centuries. Comparisons with other ancient cities highlight the challenge. Roman engineers famously built on difficult terrain in places such as Ravenna, while Mesopotamian cities struggled constantly against groundwater and subsidence. Yet Philippi managed to support monumental architecture including basilicas, forums, theatres, baths, and defensive walls in an environment that should have imposed severe limitations on long-term stability. How ancient engineers achieved such durable results without modern geotechnical science remains one of the site's most intriguing unanswered questions. The city could not have existed without water management. Ancient populations require reliable supplies for drinking, sanitation, industry, agriculture, and public facilities. Roman bath complexes alone consumed enormous volumes of water. Archaeological surveys have identified aqueduct components, drainage channels, reservoirs, and underground conduits throughout Philippi. The problem is that only fragments survive. Researchers can see portions of the system, but reconstructing the complete hydraulic network remains difficult. Sedimentation, later construction, earthquakes, and environmental change have obscured large sections of the infrastructure. Hydrologists studying the region estimate that maintaining a population of several thousand inhabitants would have required a sophisticated and carefully managed water supply. Yet the precise routes, capacities, and operational methods of many installations remain uncertain. This uncertainty creates an engineering mystery. The city functioned successfully for centuries. The evidence proves the system worked. The challenge is understanding exactly how. Some scholars suspect that significant portions of the hydraulic network remain undiscovered beneath agricultural land surrounding the archaeological zone. Others argue that seasonal water management techniques may have been far more advanced than surviving remains suggest. The result is a technological puzzle hidden underground. Standing among the ruins today, visitors often notice the apparent order of the city. Roman Philippi was organized according to a remarkably structured urban plan. streets intersected at controlled angles, public buildings aligned with major transportation routes. Commercial, administrative and residential districts occupied carefully arranged positions. This level of organization was not unusual for Roman cities. What is unusual is the terrain. The surrounding landscape is neither perfectly flat nor naturally suited for geometric urban planning. Engineers had to compensate for changes in elevation, water flow, and soil conditions while maintaining functional transportation corridors. Modern surveys using aerial imaging and digital mapping reveal impressive consistency across large sections of the city. Achieving such precision without modern surveying instruments raises important questions. Roman surveyors possessed tools such as the groma and chorobates, but maintaining accurate alignments across extensive construction projects required extraordinary skill. Even minor errors could accumulate into significant deviations over long distances. When compared with other Roman colonial cities, Philippi demonstrates a level of planning that reflects careful measurement and sustained engineering oversight. The city appears less like a settlement that evolved naturally and more like a landscape deliberately reshaped according to a comprehensive vision. Among the most spectacular remains at Philippi are its early Christian basilicas. Constructed between the 5th and 6th centuries CE, these enormous churches rank among the largest religious buildings of the early Byzantine world. Their builders transported massive stone blocks and marble columns weighing several tons each. The logistical challenge was immense. Unlike modern construction crews equipped with cranes, trucks, and powered lifting systems, Byzantine builders relied on human labor, animals, ropes, pulleys, and mechanical ingenuity. Many architectural elements appear to have been recycled from earlier Roman monuments, yet reuse alone does not explain the precision of assembly. Large components had to be transported, modified, positioned, and integrated into new structures with remarkable accuracy. Some surviving column bases and masonry joints demonstrate tolerances measured in only a few millimeters. Such precision required not only craftsmanship but also sophisticated planning. Similar achievements can be seen in Constantinople, Ravenna, and other major centers of the late Roman world. However, Philippi's location, far from the imperial capital, raises an important question. How did regional builders maintain such high technical standards despite political instability and shifting economic conditions? The answer remains only partially understood. One of Philippi's best-preserved monuments is its theatre. Built in the Hellenistic period and later modified by the Romans, it still demonstrates remarkable acoustics, allowing sound from the stage to reach much of the seating area. Without modern technology, ancient architects achieved impressive acoustic performance through theatre geometry, seating design, stone surfaces, and sound reflection. Philippi likely benefited from these same principles. However, it remains unclear whether this knowledge came from scientific understanding or centuries of practical experimentation. The evidence does not provide a definitive answer. High above the Hunza Valley and the Karakoram Mountains of northern Pakistan, Baltit Fort clings to a steep mountainside at an altitude of roughly 2,500 meters. For more than 7 centuries, this wooden and stone fortress has survived earthquakes, landslides, freezing winters, and political upheavals in one of the most geologically unstable regions on Earth. The mystery is not that Baltit Fort exists. The mystery is how it is still standing. Although Baltit Fort remained continuously known to the people of Hunza, its engineering significance only became widely recognized during architectural surveys and restoration studies conducted throughout the 20th century. Detailed structural investigations carried out during major conservation projects in the 1980s and 1990s revealed a level of seismic adaptation and environmental engineering far more sophisticated than previously assumed. Most ancient fortresses impress visitors through their size, but Baltit Fort presents a different challenge. Compared with the massive walls of Masada, the enormous stone terraces of Sacsayhuaman, or the vast defensive systems of Ranikot Fort, Baltit appears relatively modest. Yet from an engineering perspective, it may represent one of the most remarkable survival stories in ancient and medieval architecture. The fort occupies a precarious position overlooking the Hunza Valley, surrounded by some of the world's highest mountain ranges. Nearby peaks exceed 7,000 meters, while the region sits within the active collision zone between the Indian and Eurasian tectonic plates. This geological collision continues today, uplifting the Himalayas and Karakoram by measurable amounts each year while generating powerful earthquakes throughout northern Pakistan. This immediately raises the central mystery. How did a structure built centuries ago using timber, stone, mud plaster and traditional tools survive in an environment where even modern buildings require extensive seismic engineering? The deeper researchers investigate Baltit Fort, the more difficult this question becomes. Modern structural analysis has revealed that Baltit was not built as a conventional stone fortress. Instead, its builders developed what engineers today would describe as a hybrid structural system in which massive stone walls provide weight and stability, while timber frameworks are embedded throughout the structure to create flexibility. At first glance, this appears simple, but in reality it is extraordinarily sophisticated. One of the greatest dangers during earthquakes is rigidity, because structures that cannot absorb seismic energy often crack and collapse. Modern earthquake-resistant buildings intentionally allow controlled movement, and remarkably, Baltit Fort appears to employ a similar principle. The timber beams act almost like shock absorbers. When seismic waves travel through the ground, the wooden elements can deform slightly, reducing stress concentrations that would otherwise shatter stone masonry. Rather than resisting movement completely, the building accommodates it. This principle is strikingly similar to techniques observed in traditional Japanese pagodas. For centuries, Japanese builders created multi-story wooden towers capable of surviving major earthquakes through flexible structural systems. Baltit Fort, located thousands of kilometers away in the mountains of Central Asia, appears to have arrived at a comparable engineering solution, despite vastly different cultural circumstances. The question is obvious. Was this knowledge independently developed? Or was it transmitted through ancient trade networks linking Tibet, Kashmir, Central Asia and the Silk Road? Archaeologists have yet to provide a definitive answer. Even more intriguing is the fact that Baltit Fort was not constructed in a single phase. Architectural studies indicate multiple expansions spanning several centuries. Each generation of builders modified the structure while somehow preserving its overall stability. This presents another engineering puzzle. Modern renovations often weaken historic buildings because new loads alter stress distributions. Yet Baltit Fort continued to grow without triggering catastrophic failure. How did successive builders understand the structural limits of the fortress without modern mathematics, computer simulations, or formal engineering theory? No written construction manuals have been discovered, and no architectural blueprints survive. The practical knowledge behind these decisions appears to have been transmitted through experience alone. That explanation, however, creates its own mystery. The margin for error in such an environment should have been extremely small, and a single major miscalculation could have destabilized the entire complex. Another unanswered question involves the fort's extraordinary adaptation to climate. Hunza experiences dramatic seasonal variations. Winter temperatures frequently fall below freezing, while summer sunlight can be intense due to the region's high elevation. Such conditions create repeated cycles of expansion and contraction that gradually destroy masonry. Engineers today recognize freeze-thaw weathering as one of the most destructive forces acting on stone structures. Water enters microscopic cracks, freezes, and the expanding ice exerts pressure that causes the cracks to widen. The cycle repeats, and over centuries entire walls can fail. Yet Baltit Fort has endured these processes for generations. Part of the explanation appears to lie in its layered construction system. The thick walls provide thermal mass, absorbing heat during the day and releasing it slowly at night. Internal wooden frameworks reduce stress concentrations while helping distribute structural loads. Small window openings minimize heat loss during winter while limiting excessive solar gain during summer. Modern sustainable architecture frequently employs similar strategies. What remains uncertain is how medieval builders acquired such an advanced understanding of environmental performance without access to modern physics. Researchers have identified practical effectiveness, but they have not fully explained the origin of the knowledge. The mystery becomes even greater when examining the materials themselves. Some of the original timber elements survived for centuries despite exposure to extreme mountain conditions. Normally, wood exposed to fluctuating humidity, snow, ultraviolet radiation, and biological degradation deteriorates relatively quickly. Yet portions of Baltit's wooden framework remained functional long enough to support major restoration efforts. Conservation specialists believe careful species selection played an important role. Local builders likely chose timber with naturally favourable mechanical properties and resistance to decay. However, the exact methods used to prepare, season, and maintain these materials remain poorly documented. The survival rate exceeds what many researchers would expect under such environmental conditions. Then there is the question of logistics. Today, moving construction materials into mountainous terrain often requires vehicles, cranes, roads, and extensive infrastructure. The original builders possessed none of these advantages. Baltit Fort sits on a steep slope above the valley floor. Stone blocks, timber beams, tools, food supplies, and construction materials all had to be transported manually or with animal assistance. The fortress contains multiple stories, thick defensive walls, elevated watch points, and extensive living spaces. Everything had to be carried uphill, everything had to be assembled on unstable terrain, everything had to remain structurally sound afterward. When archaeologists estimate the labour requirements involved, the achievement begins to resemble other remarkable mountain engineering projects such as Machu Picchu, or the cliffside monasteries of the Himalayas. Yet unlike those famous sites, Baltit's engineering remains comparatively understudied. Its greatest mystery may be hidden in plain sight. On the northeastern coast of Greece, beside the Aegean Sea, lie the ruins of Abdera, an ancient city whose buried streets may preserve one of the most overlooked engineering mysteries of the classical world. Although known from ancient texts, the true scale of Abdera only emerged through systematic excavations conducted during the 20th century. Beneath layers of sediment, archaeologists uncovered a remarkably organized urban landscape dating primarily between the 5th and 4th centuries BCE. What they found was unexpected. The mystery of Abdera is not a lost treasure, a vanished king, or a forgotten war. It is a city that appears to have been designed with principles that resemble modern urban planning more closely than many settlements built thousands of years later. At first glance, Abdera seems unremarkable compared with famous sites such as Machu Picchu, Petra, or the Great Pyramid of Giza. Yet the deeper archaeologists, engineers, geologists, and urban historians study its remains, the more difficult a fundamental question becomes. How did a society more than 2,400 years ago create a city whose organization appears strikingly similar to concepts employed by modern planners? The answer remains incomplete. Excavations revealed a network of streets arranged according to a highly structured grid. Major roads intersected at near right angles, dividing the city into organized residential blocks. Such layouts are common today, but in the ancient world they were far from universal. Many contemporary cities evolved organically over centuries. Streets twisted around topography, expanded without centralized planning, and often lacked consistent organization. Even some important ancient settlements developed through gradual growth rather than deliberate design. Abdera appears different. Evidence suggests that significant portions of the city were planned before construction began. That creates an engineering puzzle. Before the first house could be built, surveyors would have needed to establish alignments across hundreds of meters of terrain. They would have had to determine road widths, property divisions, drainage routes, and future expansion zones. Modern engineers accomplish such tasks with laser instruments, satellite positioning systems, digital elevation models, and sophisticated surveying equipment. The builders of Abdera possessed none of these, yet measurements indicate a surprisingly consistent urban geometry. Researchers often compare Greek-planned cities to the work associated with Hippodamus of Miletus, frequently called the father of urban planning. However, even if theoretical concepts existed, translating those ideas into physical reality required extraordinary precision. The challenge becomes clearer when considering scale. A small surveying error of only 1 degree can produce deviations of several meters across long distances. Over an urban grid extending hundreds of meters, cumulative inaccuracies should become obvious, yet many sectors of Abdera display a coherence that suggests careful control over measurements. Exactly how ancient surveyors achieved such accuracy remains uncertain. Some scholars propose the use of sighting poles, ropes, measuring staffs, and astronomical observations. Others suggest techniques involving solar alignments and geometric triangulation. The problem is that no surviving documentation fully explains the procedures used. The city itself appears to preserve evidence of expertise whose operational details have largely vanished. This puzzle becomes even more intriguing when viewed alongside the city's water management system. Beneath the streets, archaeologists discovered drainage networks designed to remove rainwater and wastewater from inhabited districts. To modern observers, drainage infrastructure may seem ordinary. In reality, it represents one of the most demanding engineering challenges in urban construction. For a drainage system to function effectively, channels must maintain carefully controlled gradients. If the slope is too shallow, water stagnates. If the slope is too steep, erosion accelerates and structural damage becomes more likely. Engineers today calculate these parameters using mathematical models and precise instruments. The builders of Abdera relied on observation, experience, and tools that remain only partially understood. Yet many sections of the drainage network appear to have functioned efficiently for generations. The implications are significant. It suggests that ancient engineers possessed a practical understanding of hydraulics, far more sophisticated than commonly assumed. Comparison with other ancient civilizations strengthens this conclusion. The Romans became famous for aqueducts and sewers. Mesopotamian cities developed canal systems. The Indus Valley civilization built advanced drainage networks more than a millennium earlier. Abdera demonstrates that Greek urban engineers also mastered complex water management techniques, even though their achievements often receive less attention. Another mystery emerges from the city's relationship with its environment. Abdera occupied a coastal zone shaped by rivers, sediment deposition, and shifting shorelines. Geological studies indicate that the coastline in antiquity differed substantially from what exists today. Over centuries, rivers transported enormous quantities of sediment toward the sea. Coastal landscapes gradually transformed. Harbours silted up. Channels migrated. These processes create persistent problems even for modern port cities. Yet ancient Abdera flourished as an important commercial centre, connected to maritime trade networks across the northern Aegean. How did its inhabitants maintain access to the sea despite environmental changes that constantly threatened coastal infrastructure? The question remains unresolved. Some researchers believe portions of the ancient harbour now lie buried beneath thick sediment deposits. Others suspect that sections may be submerged offshore. The difficulty of reconstructing the original coastline means that the complete harbour system has never been fully identified. If future discoveries reveal its design, they could transform our understanding of Greek coastal engineering. The city's defensive architecture introduces another layer of complexity. Abdera was protected by fortifications extending around substantial portions of the settlement. These walls were not simply barriers. They were engineered systems interacting with local terrain. Builders adapted routes according to topography, balancing defensive effectiveness against construction efficiency. This required practical geological knowledge. Engineers needed to identify stable ground, avoid vulnerable zones, and understand how foundations would behave over time. Modern geotechnical investigations rely on drilling, laboratory testing, and computer simulations. Ancient builders relied on accumulated experience, yet many of their structures endured for centuries. The question is not whether they possessed engineering knowledge. The evidence clearly shows that they did. The mystery lies in how that knowledge was acquired, transmitted, and preserved. Perhaps the most fascinating aspect of Abdera is that nearly all of these achievements were accomplished without leaving behind detailed technical manuals. The city itself survives, but the engineers do not. Their measurements remain visible, while their methods are largely invisible. Their drainage systems still reveal deliberate design, yet their calculations are lost. Their urban plan continues to impress archaeologists, but their instruments have mostly disappeared. This contrast creates one of the most intriguing archaeological puzzles in Greece. In western Turkey, near the winding Meander River, lie the ruins of Magnesia on the Meander, a city where stone, mathematics, and human perception were combined with such precision that even modern researchers still struggle to explain how its builders achieved it more than 2,000 years ago. Although travellers had noted scattered ruins for centuries, systematic archaeological excavations beginning in the late 19th century gradually revealed the remains of a large Hellenistic city. Beneath layers of soil emerged temples, theatres, stadiums, colonnades, drainage systems, and one of the most sophisticated examples of urban planning ever discovered in the ancient Mediterranean world. At first glance, Magnesia appears similar to many Greek cities, yet detailed surveys reveal something extraordinary. The city was not simply constructed, it was engineered according to a remarkably coherent geometric vision. Archaeologists mapping the site discovered that major streets, public buildings, and ceremonial spaces followed an organized spatial plan extending across a large urban area. Distances between structures often correspond to consistent measurement systems, suggesting that planners operated using standardized units and precise surveying techniques. Today, engineers achieve such accuracy using laser instruments, satellite positioning systems, and digital mapping technologies. Ancient surveyors possessed none of these tools. Instead, they relied on ropes, measuring rods, plumb lines, observation of celestial bodies, and practical geometry. The mystery is not that ancient builders could measure land, as civilizations had been doing so for millennia. The mystery is the scale of precision maintained across an entire city. Researchers continue debating exactly how surveyors transferred measurements across uneven terrain while preserving alignment with such consistency. When compared with many contemporary settlements across the Mediterranean, Magnesia appears unusually disciplined in its design. Its organization resembles the carefully planned layouts later associated with Roman engineering, despite being conceived centuries earlier. The most famous structure in the city was the Temple of Artemis Leukophrene, regarded by ancient writers as one of the most magnificent temples of the Greek world. The building measured approximately 67 meters in length and 31 meters in width. Massive marble columns surrounded the structure, creating a visual effect that impressed visitors throughout antiquity. Yet the true mystery lies not in its size, but in its construction. Many surviving blocks demonstrate an astonishing degree of precision. Stone surfaces fit together so closely that the gaps between them remain extremely small even after more than 2,000 years of earthquakes, temperature fluctuations, and weathering. Modern conservation specialists examining similar ancient structures often discover deviations caused by settling erosional structural movement. Yet portions of Magnesia continue to display a level of craftsmanship that suggests extraordinary control during construction. How did builders working with bronze and iron tools achieve such accuracy? Some researchers believe master craftsmen spent enormous amounts of time hand-finishing each surface. Others argue that specialized measuring techniques may have existed, but were never fully documented. The archaeological evidence provides clues but no definitive answer. The result is a temple whose surviving remains continue to raise questions about the true capabilities of ancient stoneworkers. Every monumental city faces the same engineering challenge, transporting enormous quantities of stone. Magnesia required thousands of tons of marble. Some architectural components weighed several tons each. These materials had to be extracted from quarries, transported across significant distances, and positioned with remarkable accuracy. Ancient sources describe ingenious methods for moving columns. In some cases, builders reportedly attached wooden frameworks around cylindrical stone shafts, effectively transforming the columns themselves into giant wheels. While experimental archaeologists have demonstrated that such techniques could work, scaling these methods to an entire construction project remains difficult. The logistics become even more impressive when considering the limitations of the period. There were no steam engines, hydraulic cranes, combustion engines, or steel cables. Every movement depended on human labor, animals, mechanical advantage, and careful planning. Comparisons with the construction of the Great Pyramid of Giza, Baalbek, and other ancient megastructures reveal a recurring pattern. Ancient engineers repeatedly accomplished transportation feats that appear disproportionately advanced relative to the technologies traditionally associated with their era. Magnesia offers another example of this enduring puzzle. Western Anatolia sits within one of the most seismically active regions of the Mediterranean. Over thousands of years, powerful earthquakes have repeatedly struck the area. Entire cities vanished after seismic disasters, yet Magnesia survived for centuries. Excavations have revealed foundations and structural arrangements that appear unusually resilient. Certain construction techniques seem designed to distribute loads efficiently throughout buildings. Some masonry configurations may have allowed limited movement without catastrophic collapse. Modern earthquake engineering relies on detailed mathematical models, seismic monitoring, and computer simulations. Ancient builders possessed none of these resources. However, they did possess something equally valuable: generations of accumulated experience. The mystery lies in determining how much of their apparent success resulted from empirical observation and how much reflected a deeper understanding of structural behavior. Some historians suggest that repeated rebuilding after earthquakes gradually produced increasingly resilient designs. Others argue that ancient architects may have recognized principles of force distribution more sophisticated than traditionally assumed. The evidence remains incomplete, but the survival of many structures suggests knowledge that was far from primitive. Among all the mysteries of Magnesia, none may be more fascinating than the work of the architect Hermogenes. Ancient architectural writers praised him as one of the greatest designers of the classical world. His influence spread throughout the Mediterranean, and his ideas shaped generations of builders. What makes Hermogenes extraordinary is not simply what he built, but how he manipulated human perception. Modern researchers studying the Temple of Artemis have noted that many proportions appear carefully calculated to influence the way observers experience the structure. Column spacing, building dimensions, sightlines, and visual relationships create an impression of balance that exceeds what would be expected from purely functional design. This phenomenon belongs to a field now known as visual architecture or perceptual architecture. Human vision is imperfect. Straight lines can appear curved. Parallel surfaces can seem distorted. Large structures often look asymmetrical when viewed from ground level. The builders of the Parthenon in Athens famously corrected such optical illusions by subtly curving lines and adjusting dimensions. Evidence suggests that Hermogenes employed similarly sophisticated strategies. The question is how? There is no surviving manual explaining his methods. No complete mathematical treatise describes the calculations behind these effects. Yet the architecture itself suggests an understanding of visual psychology that feels remarkably modern. Today, architects use computer simulations to predict how people perceive buildings from different viewing angles. Hermogenes achieved comparable results using nothing more than geometry, observation, and experience. Some scholars argue that his designs represent one of the highest achievements of ancient architectural science. Others believe his methods may reflect knowledge accumulated over centuries and later lost. Whatever the explanation, the visual perfection of his structures remains one of the most intriguing unsolved puzzles of classical architecture. Magnesia also featured a massive stadium designed to hold large crowds. Its layout showed advanced planning for movement, visibility, and crowd control. Entrances, seating, and viewing angles were arranged efficiently, demonstrating impressive engineering despite the lack of modern design tools. How ancient planners achieved such effective layouts remains an open question. Northern Greece, around 60 kilometers southeast of modern Thessaloniki. Beneath quiet fields overlooking the Gulf of Toronius lie the remains of a city destroyed in 348 BCE. Unlike many ancient settlements that evolved for centuries, ancient Olynthus was frozen in time. What archaeologists uncovered was not merely a Greek city, it was a technological snapshot of an urban civilization whose engineering sophistication may have been centuries ahead of what historians once imagined. Although the ruins were known locally for generations, systematic excavations began in 1928 under American archaeologist David Moore Robinson. Over the following decade, researchers uncovered more than 100 houses, streets, drainage systems, workshops, public buildings, and some of the finest pebble mosaics ever discovered in the ancient Greek world. The city had been destroyed by Philip II of Macedon in 348 BCE and was never substantially reoccupied. As a result, Olynthus preserved an unusually complete record of urban life during classical Greece. The significance of the discovery became increasingly apparent as excavation reports accumulated. Unlike Athens, Sparta, or Corinth, whose ancient layers were repeatedly rebuilt and altered, Olynthus offered archaeologists something extraordinarily rare: an entire city preserved almost exactly as it existed at the moment of destruction. Every street, every courtyard, every drainage channel, and every decorative floor became evidence in a much larger mystery. How had a society working more than 23 centuries ago achieved such remarkable levels of standardization, planning, and technical precision? The first puzzle emerged from the city's layout itself. Olynthus was organized according to a remarkably regular grid system. Streets intersected at near right angles, creating blocks of housing that followed repeating dimensions across large sections of the city. Today, creating such a layout appears straightforward because surveyors possess satellite positioning systems, laser instruments, and computerized mapping software. 4th century BCE engineers possessed none of these technologies, yet measurements conducted by modern archaeologists revealed levels of consistency that continue to attract attention. Residential blocks often approached 100 meters in length while maintaining remarkably uniform proportions. Similar urban planning principles existed elsewhere in the Greek world, particularly in cities influenced by Hippodamian planning. However, Olynthus represents one of the best preserved examples ever discovered. The mystery is not that the Greeks understood geometry. The mystery is how they repeatedly translated geometric theory into large-scale urban reality across uneven terrain with such consistency. Some researchers suggest that surveyors relied on ropes, wooden stakes, sighting instruments, and astronomical observations. While these methods undoubtedly played important roles, modern attempts to reconstruct the entire planning process often reveal how difficult maintaining accuracy becomes over long distances. Small errors accumulate rapidly, yet the urban framework of Olynthus demonstrates a level of control that appears surprisingly advanced for its era. The city's residential architecture deepens the mystery. Excavations uncovered dozens of houses sharing remarkably similar internal arrangements. Courtyards occupied comparable positions. Rooms followed recurring patterns. Entrances, storage spaces, workshops, and domestic areas frequently appeared according to standardized principles. Modern urban planners would describe such repetition as modular design. The concept is common in contemporary architecture because standardization reduces construction costs and simplifies planning. Seeing similar principles emerge in a classical Greek city raises important questions. Did Olynthus possess formal architectural guidelines? Were builders working from standardized measurement systems now lost to history? Or had generations of craftsmen developed practical construction formulas capable of producing extraordinary uniformity without written technical manuals? Another mystery lies beneath the streets. Olynthus possessed an extensive drainage network designed to manage rainfall and wastewater. Archaeologists uncovered channels running beneath roads and between residential districts. These systems directed water away from populated areas while helping protect foundations from erosion and flooding. Hydraulic engineering may not sound mysterious at first glance, yet modern engineers understand that drainage systems function properly only when gradients are carefully controlled. Too steep and erosion accelerates. Too shallow and water stagnates. Maintaining appropriate slopes across an expanding urban landscape requires careful planning and accurate measurement. The drainage network of Olynthus functioned effectively enough to support a substantial urban population. More than 2,000 years later, portions of the system remain visible, providing evidence of engineering decisions that continue to impress specialists. The challenge is explaining how such precise hydraulic management was achieved using tools that appear technologically simple by modern standards. The mystery becomes even more intriguing when examining environmental adaptation. Northern Greece experiences seasonal variations in temperature, sunlight, and wind patterns. Many houses at Olynthus appear designed to take advantage of these natural conditions. Courtyards improved ventilation. Building orientations maximized winter sunlight while reducing summer heat exposure. Covered walkways created transitional spaces that moderated temperature changes throughout the day. Computer simulations performed on ancient Mediterranean architecture suggest that passive climate control strategies can significantly improve indoor comfort. Similar principles are celebrated in modern sustainable architecture. Yet Olynthus demonstrates that builders may have understood aspects of environmental design more than 2 millennia ago. Whether this knowledge emerged through scientific observation, accumulated experience, or cultural tradition remains difficult to determine. Among all the mysteries of Olympus, however, none is more fascinating than the city's extraordinary mosaic floors. Today, visitors often admire mosaics primarily as works of art. Archaeologists see something more. They see evidence of geometry, planning, material science, visual mathematics, and construction techniques that remain surprisingly difficult to explain in full detail. The finest examples at Olympus were created from carefully selected pebbles, rather than the cut tesserae that became common in later Roman mosaics. Craftsmen arranged thousands of stones to form complex geometric patterns, mythological scenes, animals, and decorative borders. Some mosaics display astonishing symmetry. Others contain intricate curves and repeating motifs requiring precise spatial control. The challenge becomes apparent when considering the construction process. Builders worked without graph paper, digital modeling software, laser guides, or modern measuring equipment. Yet many designs maintain proportional relationships across large floor surfaces with minimal visible distortion. Researchers have long debated how these artisans achieve such accuracy. One possibility involves the use of geometric grids laid out directly onto prepared surfaces. Another proposes the use of string frameworks functioning as temporary reference systems. Some scholars suggest artisans may have employed full-scale preliminary drawings, similar to methods later documented in other artistic traditions. The problem is that direct evidence for these techniques remains limited. The temporary tools would have disappeared long ago. What survives are the finished floors themselves. They reveal the results of a process, but not necessarily the process itself. Comparisons with contemporary civilizations make the mystery even more compelling. Egyptian builders mastered monumental stone construction. Mesopotamian cities developed sophisticated urban systems. Persian engineers created vast imperial infrastructure. Yet the pebble mosaics of Olympus represent a unique intersection of mathematics, aesthetics, and technical execution. Their precision rivals decorative traditions that emerged centuries later under the Romans. Some patterns demonstrate rotational symmetry and geometric balance that modern observers can easily recognize, but remain difficult to reproduce manually without careful planning. Experimental archaeologists attempting to recreate comparable pebble mosaics often discover that maintaining consistency across thousands of individual stones demands exceptional skill, patience, and spatial awareness. What do you think was the greatest achievement of Olympus? Its advanced city planning, its remarkable drainage system, or its astonishing mosaic craftsmanship? Share your thoughts in the comments below.